Yes, okay. Good morning, everyone. So welcome to the session on Wednesday in the morning. So just to announce, there is a little bit change in our program. So I will chair this session in the morning, but in the talk at 12 o'clock, this presentation will be shared between Professor Ruffini and Wang Yu. So there will be two presenters for this talk. So we start our presentation with Lipунov, Extreme Universe. Oh, please.
First of all, thank you very much for the organizers, scientific, local, and Remo Ruffini, especially for the invitation for the very big auditorium. And thank you very much. I am started. I have the more or less small, but not very small introduction. What does it mean, extreme universe? Because 20 years before, I was a theoretical man, fully, no experimental. And but I thinking that I must to do new astronomy region is a fully robotic telescope astronomy. Why? Okay, I found my. All slide here with the stars that is receiving called the master telescopes. This is our image. And that my co-authors. The different observatory because around the world. And that is a friend and participant of the master on the conference, old conference, 15 years. The Victor Kornilov is my friend, and we study. Unfortunately, he died now, but all project will I show. I preparing with Victor. So we started with this paper published by Einstein very soon after the discovery of gravitational relativity. And he introduced very interesting value, natural luminosity. Here's look, see that is a luminosity formula, Einstein formula for the circular orbit. The distance A, the mass M1, M2. But inside the formula have the fundamental value. The Einstein called this natural luminosity. Very interesting, this value is equal to the Planckian luminosity. Exactly, the Planck constant disappear. But for astrophysics, it's very important this formula, maximal luminosity, which we can found from the relativistic object. You see the same. That's very important value if you come to astronomy and thinking how to see the relativistic universe, stars. For understanding, a lot of time ago, we, with my friend Victor Kornilov, applied the Monte Carlo simulation method for the simulating relativistic universe, a binary system with relativistic stars. You see, we used a computer with a memory 4 kilobytes at that time. But we found a lot of interesting objects and artificial. That is principal scheme, the initial distribution, usual evolution scenario of normal star, the thermonuclear evolution, and evolution magnetized star, which most all received result in the Zeldovich team. Sometimes to the Moscow comes Kip Thorne, and one time I told him about the scenario mentioned, that is population synthesis programs. And he asked me how often the neutron stars merge in the universe. We published this first paper which predicted the merging rate of neutron stars and the background gravitational wave radiation from the binary galaxy stars. That's very important for the, if you want to see the cosmological gravitational wave, you must know the interval of frequency where it's see. That's our team.
Thank you.
A lot of people around, about 10 people. And now they, I'm sorry, why? Oh, mamma mia. Yes, answer. Next, we receive next answer. That is, you see the merging rates for 3 reactions per galaxy, like to have the salpeter function of the birth rate of the stars as our galaxy. That is salpeter function for the Milky Way galaxy. But you see, it seems that the first discovery it must be black hole binary, because the horizon of detector is much more. And we published it in 95, the gravitational wave map. You see, and predicted the whole sky gives us 3 measurements per year if the interferometer have horizon 50 megaparsec. 50 megaparsec. But in 20th century, no people up to the end of 20th century, no see the relativistic merging process. Why? That's a very simple question, answer, because you see that the 19th century photo of the main prospectum in Paris, never people around. People is a transient, very fast moving, and disappear from the old photographic technica. The same situation, you see only one man which stay here, because exposition about 10 minutes maybe on the first photo, they exist. But the same situation we see in 22nd century, but what we see now, because appears the detectors, fast detectors, and so on. By the way, you see that luminosity, that is a lifetime. That is a 1 second. That is 1 second. That is Hubble time. You see the luminosity of blazar, quasars, pulsar is very small. Is very small, but much more bigger the gravitational wave, long GRB, short GRB, and some another, and of course gravitational wave. By the way, everywhere I listen that the discovery Lorimer, I know Lorimer maybe 40 years when he come to the astrophysics, because we have a lot of discussion about the velocity of pulsar. And we published and predicted millisecond fast radio bars in the universe. Before merging, if you take the crab pulsar and put the orbital period 1 millisecond, you can see this pulsar from several 10 megaparsec, 100. That is a formula you can see. That is a Poynting equation used here. That another diagram, very important, about the formation magnetar. That is magnetar, upper the white dwarf, polar, extremely magnetized white dwarf, directly produced the magnetars. But not all white dwarf, very, very magnetized. About GRB, Remov want GRB, and I started about GRB. Very quick review. Energy. We see this energy of gamma ray burst. Typical collapse has the same energy. Firstly, used this by Blinnikov and more correctly Paczynski. You know, this road is for young men. You see a lot of years ago, people understand spectrum, no problem. 1 month, typical collapse temperature, the 2 electron energy mass. Duration problem, because we observe it very long event, but typical collapse time is 7 orders lesser. That is question of the gamma ray astronomy, gamma ray burst astronomy. Solution. One solution, that is a model of spinor, and depending from the moment of the magnetic field dissipation, or disk accretion on the west, usually we use this model. That is my opinion, that the real rate supernova divided to rate of GRB with supernova maybe, but not important here. A well-known picture. That is first scenario, loosely for prior, which we listened yesterday, Hartmann. And our scenario 10 years before, which produced merging of neutron stars. Neutrons are the core. That is a small history scenario we proposed for this gamma ray burst. That real calculation included all relativistic effect. You see flat 10,000 second flat X-ray emission from the GRB. That's some table of Mendeleev table. So how to see this? We constructed 20 years ago, we start to construct a fully robotic telescope. No people around, because very short events. Now we have telescope almost all continent, about 8, so 9. And you see, we can look the south and northern sky. That is first telescope in the Kislovodsk, Moscow University. That is Bruce. That is a very interesting telescope. He has a 3 axes, and he has the polarizators and color filter. And they can move parallel, not parallel, because no time. That is our photometer, which constructed by Victor Kornilov. That is first light on the Canarian telescope. That is the architecture. 50 different robotic data inside, large server and so. The typical white, our image. The Hubble less than the head of the horse. Hubble, for example, telescope. And the most important now, oh, mamma mia, I don't check in this, yes? Okay. The first most important, the illustration of our soft, which automatically found object, undefined object on the very big square degrees region, up to the 20 magnitude. And that is a very independent discovery kilonova. And that is our telescope. All telescope is same, indifferent. You see, especially the very fast telescope give us the possibility to observe gamma ray burst, very early observation, the most observation of the prompt emission from master, and the very genius project of Karl Akerlof. And that I come to the most important 3 results. That's the first very important result. You see, we started imaging gamma ray bars 20 seconds before main pulse. At this magnitude, that is second. That is a very wide field camera, not telescopic. That's very wide field cameras and another equipment. You see, we participated in the multi-wave observation, and we discovered a polarization in prompt emission. Rose, violet color. Oh. They're very interesting that there are three events. Most important, this, of course, very interesting, this one, some maybe pulsation, maybe probably. And we have published the model of this object in the spinar paradigm. You see another robotic telescope. The Swift trigger not published, but come to our internet server. But first telegram published by Master. After that, natural publishing of the Swift. Very quickly reacted telescope. Another very interesting this event, and we discover, people know this bars, the probability 1 per 1,000 year to appear if they all okay, all natural, all usual, but not all usual. And some people say, and Nico, author of this paper, of course, but you see master point, the first optical point gives a jet break in the optical. And we proposed the very complex structured jet. And master observe sky without any alerts and give alert. Yellow is a give alert of master. All most bigger telescope around the world observed our. We discovered 10 different type of astronomical objects, from the kilonova to the dangerous asteroid. That is very important. Why I say global master net? If this all sky, that is some transient discovered by master independently of alert. You see, northern telescope has the empty square, but we installed 2 telescopes in the south, and you see now this, just a moment, we see global, the comets, asteroids, you see always fully covered. There's a global net, south and northern sky. So the South Africa, a lot of transient discovered for 10-meter telescope. Okay, this discovered unwaitable. You see that the Zwicky project discovered some decreasing optical flare, but we received 6 points before. We received 6 points before, and we applied our discovery. And you see that is the most beautiful optical light curve which observed last maybe 20 years, so 25 years. Most beautiful. You see differences several order on amplitude and in time. But we analyzed time and flux and received universal curve, very universal curve, and applied to this orphan transient and found that as a maybe not GRB, not no JGB. Okay, we now connected with all big physical experiment like to the neutrino, of course, gamma ray burst and gamma Fermi blazars and LIGO Virgo gravitation wave souls. And now I see first discovery, very short correlation between detection of neutrino and optical. That is a picture published in Astrophysical Journal with a Russian flag, I'm sorry. And Ice Cube gives the alert, and after, during the minutes, we have the photos. You see, yes, you see, that's real photo. After minutes, that is blazar, that is reference stars. That is blazar. That is blazar after 2 hours. Equal. The very high energy changed during several hours correspond to neutrino detection. That's our theoretical note. That's recently we discovered the same events with the 4 detected neutrino, different equipments, but now in press, in editorial process, in the monthly notices. You see here, this neutrino, that is our observation, that is the ASAS observation. Gravitation wave, very quickly, last slide, I'm sorry. No, there's no optica here, but we predicted the black hole is first the object detected by LIGO, and we have the Russian Academia Premier medal, not medal, I don't know how to say it correctly, for this prediction, and we have that's our you know this picture. That's our 80% of all observation was done by master for the first gravitation wave. That is discovered by master 3 transient inside the book after the several days. I keep turning our laboratory 1 year after discovery and ask, you see, please, all discoveries of optical emission. Why is this very important? Because optical localization, 1 billion RAS to do the smaller error box of gravitational wave, 1 billion times. By the way, the David Ritz come independently 1 month before, and same on our desk. Localization, that real situation of gravitational wave astronomy. 1 degree is very a lot of square seconds, a lot of billion. That is very important master discovery of the kilonova. That is image from the Astrophysical Journal 2. And you see 6 telescope which independently receive image of this object. I'm sorry. Does not work. Okay, this secret slide. But I come back to our prediction 20 years before. We predicted 3 per year, but LIGO O2 observation duration 1 divided 3 of year. So discovery only 1. We predicted 3 per year, but LIGO discovery 1, but shorter time. You see that as a probability on the sky. These are our postgraduate students. The Nobel Prize. Everywhere I say, where is Pustovoid? He predicted, he published a paper for with Gerstenstein and Pustovoid, proposed it in 16 years, we must use it laser detectors. Nothing. Where is Gerstenstein? No, the problem that the Gerstenstein not live, but Postavoit live. He now died. He also died. But at this moment he is dead. He is dead. That is a very important paper. Young people must be reading. He was the main result that you must, if you want to discover a gravitational wave, you must use it. Relativistic body. Light is relativistic. So keep torn about no. No, that is maybe people look. I see this people before publication because we work with the LIGO. In this, we was between 10 principal author of the localization paper, very a lot of reference. That is now plan of LIGO very. And next one, we try to discover a black hole in kilonova. My dream to see this, we predicted the distance about 200 megaparsec, but we need a telescope 1 meter Remo, the Nobel Prize. Okay, that is a new set of the LIGO. I show you, for example, nova. What is this kilonova? That is nova in the Andromeda galaxy discovered by Master. You see, but kilonova 1,000 more powerful. Okay. Recently, at 15 years, we discovered a major asteroid with period 2 years in diameter 1 kilometer. I proposed and now the asteroid called the Svarog. Svarog is very dangerous word in Sanskrit, means sky. In Russian and Slovenian people have the gods Svarog, which preparing the sun, planet, and so by the. Okay, I finished it. That is a short review. I published it with co-author, very big, 700 pages monograph. Yeah, several months ago appeared on Russian language, and maybe very soon appear. That is a principle of the robotic observatory. That is a theoretical. That is observation and this discovery. No, most important discovery. That's all. Thank you very much. I translate.
Thank you for this very nice presentation and for being in perfect time. So we have time for questions. Questions?
What is the meaning of a orphan gamma ray burster?
No, I mean detected. What you mean?
Oh, you said orphan.
One.
Where?
In your presentation, there is orphan gamma ray burst.
Orphan. No, I am sorry. My English is not good. That is optical. Optical transient without any gamma ray burst. We discovered it on the growing these optical flyers, and we interpreted it by our previous theoretical, not theoretical, that's phenomenological formula. Very, very nice too. We imagined 4 hours before Zwicky, our project 5 million rubles, $5 million only. All.
Okay, thank you. Another question? Okay.
Is Master participating in any of the international networks like Treasure Map or Sky Portal in order to coordinate the follow-up of, big error areas in the sky. And can you comment on the prospects of master matching up with the sensitivity of the present gravitational detectors? For example, you quoted looking out at 300 megaparsec. Does it have the requisite sensitivity in order to look out for kilonova at these distances?
300. 300. We now introduce 4 telescopes. I'm sorry. Recently, last 5 years, we not receive money any from Russian Academy of Science. But we now constructed 4 telescopes of 60 centimeters with maximal magnitude limited for automatical determination transient 21. That is a predicted 21 magnitude for the kilonova at this distance. It's very simple, very calculated maybe 20 years ago, people. And
Thank you. Let's thank the speaker once more.
okay.
Okay, now we move to the next speaker. His map of the entire X-ray sky, X-rays in this variability over time, Professor Rashid Sunyaev.
Yes. Is it possible to show my slides?
Can you open the slides? This pointer is not working, the pointer over there.
Do they have problem? Oh, okay. Now I see my slides, and therefore situation is much easier. I will speak about the map of the whole sky. Norik, could you show me how to?
This not, I'll take
Okay.
another one.
Yes, but I will speak about this. On the right, you see the map of the sky, which we got after half a year of scanning of the sky with eRosita. Now we have now 4.38 scans of the whole sky, and I can say you only that we have more than 2 million quasars on this map. You see them small white points. 1 second. See? Okay, everything is fine. And everything is done with the help of eRosita, SRG eRosita observatory. And I can tell you also that in 3 days, there will be the 5th anniversary of the launch of this observatory, which is working. Observatory works absolutely fine, and RTX, one of the devices, is properly working 7 days per week, and how to say, whole year. All these 5 years, they were working at this many, at least 20,000 of observations, days of observing. I can show you now here several, just from the beginning, the advertisement. And this advertisement, this plane of our galaxy. There are eRosita bubbles. We had many conversations with Remo about this. You see it here. This is in the X-rays, and many, many point sources. And these are millions of quasars. It's impossible to see on this map whole million which we have, but there I will show you when we amplify the picture. For example, LOFAR radio instrument discovered new radio galaxy, and they asked me, are the X-rays from this object is a group or cluster of galaxies around. We discovered this cluster, but you see this beauty, and this is one of the points here. And this is, you know, at several hundred megaparsec from us, this beautiful object, which is structure of the shock waves which radiate in the synchrotron radio emission. We see this, and every point when I have no time to say about everything. I show you several examples. People are telling there is something interesting. We just go to this map and we are discovering these objects in X-rays or giving very stringent upper limits to the X-ray luminosity. Okay, and this here is shown from the beginning. I will be speaking a lot about the scanning of the sky. Look, we are scanning every day one strip on the whole sky. How to say, the ring around, and width of this ring is one day, you know, 1 degree. Every day we are covering 360 degrees on the sky, and we follow the sky every day. Our axis of rotation is moving to 1 degree. Okay, let's go further. This is the observatory, how it is flying now. You see here are two X-ray telescopes. One telescope is for the standard X-rays from 4 to 30 keV. Its name is Arctic Sea, named after Mikhail Pavlinsky. Some of you know the name of this person who in reality was leading the creation of this telescope. And it was produced in IKI, Space Research Institute in Moscow, in All Russia Nuclear Center in Sarov, and Marshall Space Flight Center supplied us with X-ray grazing incidence mirrors. Our mirrors were ready, but how to say, Marshall was producing a little better mirrors, therefore we accepted American mirrors finally. This is for this instrument, it weighs 350 kilograms, and as I told you already, this device is working already 5 years, practically every day, and giving a lot of information, mainly about transients, also about gamma burst. He is Alexander Lutavinov. He gave the talk on one of the sessions, and he also can answer your question if you have such question about the observations of gamma ray burst and about observations of transient, bright X-ray transient. Second instrument is eROSITA. This is this instrument. It is only 3.5 meter long and wide for 9 meters from this point to this point. You see also these dimensions. And eROSITA has several parallel grazing incidence mirror systems and 7 X-ray CCDs in the focal plane of every mirror system. And I will not speak, but here we have mirrors, paraboloid and hyperboloid mirrors, coated by gold, and this is focusing optics. It's working very excellent, and it simultaneously observes 1 square degree on the sky. And this is also very good. This is a wide field telescope, and 1 pixel is 9 arc seconds to 9 arc seconds. But because we have 20 or 100 or 1,000 photons from every object on every scan, we can localize our objects with precision of few arc seconds on the sky. And then best optical instruments can also localize these objects and check what they're doing. And this is the launch date. It was 17th of July, 2019. And today, yes, it was 13th of July. Therefore, in 3 days, it will be five years after the launch. Let us go to the next slide, please. I can do this myself, I hope. Yes. This is our orbit. This was our spacecraft is flying practically on the same orbit as WMAP and Planck cosmology spacecraft were working. And our orbit is practically identical to the orbit of James Webb Telescope. Only the planes of our orbit are a little shifted, but center is every time on the, oh, excuse me. Yeah, you see here L2 point. This is second Lagrangian point, and we are on the halo orbit around, and one revolution around L2 point, Lagrangian, second Lagrangian point, we are getting one full sky map, and this every half a year. And we were flying, this is direction to the sun, Earth and Moon are always from one side of our spacecraft. And this is good for from many reasons. And distance from Earth to L2 point is 1.5 million kilometers. Therefore, it is good. And you see here the moon orbit. Round, it's not really round, but you understand immediately how big is distance where we are working. And we are working 5 years already on this orbit. Let's go further. I told already to you that we are observing the big scans on the sky. You see it's written here, and our axis of the spacecraft, main axis, is we're rotating around it. It's directed to the Earth, to the radio dishes and sun, which are close from this direction. And we rotate 6 times per day around the axis. Every 4 hours, we return to the same source. And we are observing every source once per half a year during a day. 6 times, and there is beautiful timing. We have every source of the sky is observed 6 times per day, once in a half a year. This permits to look for the short time variability of million sources on the sky. We can see how they change during a year. Okay. This is a map. I told you about X-ray map. It is in 3 colors here. I will tell you about these colors. And total band is from 300 electron volts to 2.3 keV. And this is the center of our galaxy. This is the brightest objects in the sky, Scorpio X1. This is Cygnus loop. I will show also map. But I told you also about this millions of the point sources which we discovered, and we will present full catalog. German site already presented the catalog on the half of the sky, but only after first scan of the sky. And I told you that we have 4.18 scans of the sky. Let's go further. In 2007, Russian Space Agency and DLR, German Air and Space Agency, made the statement and included into the memorandum of understanding that for the data processing and publication of the results of the maps on one half of the sky will be responsible Russian scientists, Space Research Institute in Moscow, and German scientists will be responsible for results from another hemisphere. And we were sharing this data and publishing them, and you see this is, again, I make the same mistake. You see here no, it's impossible. You can see here, this part is MPE part, Max Planck Institute for Extraterrestrial Physics, this part of the sky, and this half of the sky is processed in Moscow and also in Garching with our group. You see here, and it's interesting because also there are some differences on the sky between these maps. Here you see most interesting clusters of galaxies, black holes, and neutron stars, bright neutron stars in our galaxy on this map. You see Coma cluster of galaxy, Virgo cluster of galaxy, Shapley supercluster. You see here, this is large Magellanic Cloud. We can see where we see hundreds of X-ray sources just in Magellanic Clouds. And you see the Cygnus loop, Cygnus X1, well-known black hole, and there are many, many other interesting objects on the sky. Orion nebulae, these are plenty of young stars. And we are looking for young stars, and these young stars are rotating, and we see variability of them every, how to say, for hours or every half a year. It's possible to do. You see this, and I wish to show you this map where it is first map, 400 millions of photons, X-ray photons. And we measure for every photon exact time when it came, exact direction with precision, few seconds, and exact energy. CCDs are excellent, German CCDs. We have 7 CCDs for each of the mirror systems. Everything is working till now properly. And this is RGB red, this green and blue map. All 400 million of photons detected during half a year are on this map. And what is important, that red color corresponds to photons with energies from 300 to 600 electron volts. These are cold objects. Their temperature is only few million Kelvin. Many stars are very bright in this band. Green is corresponds to the energies of photon from 0.6 to 1 keV. This is tens of million Kelvin. And blue is from 1 to 2.3 keV, which is, 20 or 30 million Kelvin temperature. Today, this is important. On this map, we see 400 millions of photons. After 26 months of the scanning of the sky, we have more than 1.5 billion of X-ray photons on the same map. And we have correspondingly 4 times more objects on the sky. And we know a lot about variability. And this is great because if you show all 4 of these maps, they're blinking. You see that whole sky is blinking this enormous amount of transients. And in a half year, we have every day, we are discovering more than 10, 20 objects which became during half a year brighter or dimmer 10, 20, or 100 times. It is a lot of work, and obviously we should make are working on the catalogs of these variable objects. Oh, excuse me. Yes. I think this is good. Marat Gilfanov, who is, how to say, member of our conference and one of the organizers of the sections, he presented here the region, the half of hemisphere from 0.3 to 0.7 keV. This is it, and from 0.7 to 2.3 keV. Here, enormous role plays the absorption of neutral hydrogen and dust in our galaxy. And therefore, we see that the plane of galaxy is absolutely dark, except enormously bright object like Cygnus loop. You see here black, this and this. This is just absorption of X-rays. Here radiates halo of our galaxy, hot gas, and I will show you, we now see the supernovae which exploded in that, and we see the rest. We can measure what is the density and temperature of plasma around where the supernova remnant is decelerating. It's beautiful paper. And on this map, at higher energy, 0.7 to 2.3 keV, there is practically invisible absorption on neutral hydrogen. You see this plane of the galaxy. Here, nothing is coming from that region. And here, this region is full by the X-ray sources. In addition, now halo of our galaxy is weak because it's low temperature. It's red on the previous maps, and we see these millions of the extragalactic objects, extragalactic, and there are millions plus nearby stars. A lot of nearby, hundreds of thousands of nearby stars with coronae 1,000 times more bright in X-rays than corona of our sun. Enormous activity. Let's go further. And this is great and unexpected discovery. This was the blue color. It's Rosetta bubbles around this map plane of our galaxy. Plane of our galaxy as we see it in the hundreds of MeV and GeV gamma rays by Fermi spacecraft. You see this red. Plane of the galaxy radiates due to the pi zero production and decay of the double photon decay of the pions. And also there are Rosetta bubble, which is observed on the south from the galaxy and in the north. We see also, this is the Fermi bubbles. But what is our discovery? Our discovery is this blue part. Rosetta sees a lot of shock waves. We see thermal plasma. We measure chemical composition of the gas erupted from the galaxy. You see it here. And this is very impressive. We compare, obviously, our maps with the North Polar Spur. You know, there is a part of this upper part is well known by, I think the Dutch radio astronomers discovered this after the war. So bright is this North Polar Spur. But we see it also similar things on the south. I have no time. We have several papers now ready for publication about the properties of this object. And just for you, I can tell you that we have now maps of these Rosetta bubbles in the lines of different elements. For example, in the hydrogen-like oxygen with only one electron. And helium-like oxygen with 2 electrons only, and we see magnesium, hydrogen-like magnesium, helium-like magnesium, we see neon. You know, it is beautiful images, and we see how where are the shocks with corresponding temperature and overabundant in a given ion. It's extremely nice and interesting atomic physics, high temperature ionic physics. Yes, this is sketch, how we consider it. It is Fermi bubbles, simple picture, and this is Rosetta bubbles. I can tell you this paper of 2020, and obviously our views now, because we have much more data, views are slowly diffusing, and we are not so strong in our statements. I can say also. Let's go further. This is beautiful galaxy, which I showed you in the beginning. It was discovered by LOFAR in the sky. They were just scanning the part in giant interferometer. They were looking to this, and this object just reminds me M87, because very old pictures of M87, giant galaxy gigacluster, and we see there are shocks. But this system is older. And we see several explosions of the galactic center. Galactic center is here, and we see a lot of X-rays around. And there is counter jet in this direction. Main jet, as in M87, is going up, and you see the shock from previous explosions of the nucleus. It is so beautiful. Its paper is published in Nature Astronomy long ago, but I think that you easily find it. But I can tell you the recent sensation, everything was published, is a telegram, which we published on 16th of April. Gaia, great spacecraft, which is also working now already many years near the second Lagrangian point. Gaia is ready now to demonstrate the long list of the binaries which they resolved and know exactly what are the masses of all components. And there are rumors that they have thousands of objects which are enormously, how to say, precisely measured, and which are maybe black holes. They published 3 black holes. I will not speak about 2 which have masses 5 or 7 solar masses. It's not so interesting. There is one black hole which has mass 32.7 solar masses. It is black hole in binary system with the sun, which is a red supergiant as red subgiant as our sun. And you can see that, not subgiant, dwarf. And you can see there, they investigated the motion of that star with mass 0.76 of solar mass, and radius is 5 solar masses, solar radii, and surface gravity is very small. But what is important, temperature is very close to the solar, and metallicity is practically 3 orders of magnitude below the metallicity of our sun. They know this, but due to tiny deviation in the orbit of this star, they found, just using normal Newtonian mechanics, they found the star, hidden star, which is 33 solar mass and which is absolutely invisible in optical light. We immediately looked to the coordinates because they became open, looked to Rosetta map, and we found that there are no X-rays at all from these objects. And upper limit, a lot of people who here are relativistic astrophysicists, they know what means Eddington luminosity. It is, how to say, many bright X-ray sources are radiating near, or they're brighter than 1 or 10% of Eddington luminosity. Some of them several times are brighter than Eddington luminosity. This our upper limit is 10 in power 10 Eddington luminosity for this object. 10 in power minus 29, we know distance to this object. It is enormously dim, and this is great because now Chandra is trying to find what is there. But we immediately just look into our map, thought, okay, this is our upper limit. We can go further. I do not speak, at least Professor Mirabel knows what is the Lockman hole. This is Lockman hole in X-rays, just no absorption in 21 centimeter. And here we have 6,000 X-ray sources on 20 square degrees in the Lockman hole, and 200 extended objects, and we found, and now confirmed by optical observations, 185 clusters of galaxies here. And there are many additional things about this scan. This is a scan in 20 degrees from the center of our galaxy. I can show what important we see. This remnant of supernova remnant, rather, because it's yellowish, it has a rather high temperature, but not very high. Very high temperature is coming from that green object, SNR, another supernova. And there are many other supernovae which are much more red, they're old. You see the T Tauri star, just one bright T Tauri star. You see here huge star-forming region. We see immediately more than a dozen of stars, young stars there. And every place where we see enormous amount of sources of completely different nature. You see there are pulsars. This is a pulsar, this bluish picture, PSR 1883. For all pulsars on the sky, we now have X-ray luminosity or upper limit for the X-ray luminosity, because we have the map of whole map, very good map of the sky. I can show you, I told you about lines. This is great resolution of the spectral resolution of X-ray CCDs, and this Cygnus loop, 400-second observation per pixel, just scan. Very rapid scan through the
Cygnus loop. And you see, we see hydrogen-like oxygen. This is iron L-shell X-ray lines, neon helium-like line, magnesium silicon line, very bright. We see this immediately, and we can give you map in every line of this. This is the SN87A. Yesterday there were several talks and mentioning this beautiful supernova remnant, which explodes on our eyes. And you see again, this is a red picture, this is XMM long observation, and this is short observation of Erosita, black. And you see in neon, we see both helium and hydrogen like line. It is enormous. And just as an example, these are two relativistic jet NSS 433, another X-ray source, and you see one recessive jet and another, how to say, approaching jet, and we see a lot of iron, silicon lines, neon lines, and this is great instrument, I can say you so. This is the same spectrum. This is how we were scanning. We discovered a lot of quasars with redshift more than 5. Just we are, if we have time on the big telescope, we immediately discovering what is the redshift of quasar. We have millions of quasars. And you see one of Pavel Medvedev discovered X-ray, extremely bright X-ray quasar at redshift 6.18. All lines shifted in the spectrum more than 7 times. This is just one of the spectra for quasars of 5.02. And you see Lyman alpha line, and it comes to now, it has wavelengths 1,200 angstrom, but coming to us at 7,500 angstrom, because redshift is 5. And you know, it is just, you look to any object and you have enormously interesting things. This is redshifts from all literature, all existing data from 140,000 quasars on the 1/2 of the sky. We have million for 140 people have estimates of the redshift. And you see redshift at redshift 6, many of them we measured ourselves what is a redshift. Okay, I will go further. Now about variability. I will talk mainly about variability of these points after 4 scans of the sky. You see here, half a year ago, we observed here no one photon from the point where there is a cross. After half a year, we have enormously bright objects here. Enormously bright, nothing there, and hundreds of photons from here. And we know that this object is TDE, tidal disruption event case, when the unclever star you see here is going too close to black hole, like the stars which are observed by Gensel and Los Angeles University group. And you see it's coming here, and then this star is disrupted. Part of it is going, matter is going to infinity, part is captured, and enormously bright X-ray source is appearing there. We are working very close with Sri Kulkarni, with Zwicky Transient Facility. It's interesting that we see now that there are 2 families, one family which is more bright in X-rays from the beginning, and then optics appeared, and another where optics is coming ahead and X-rays appeared later. Yes, I think that, yes, this is a great thing. Clusters of galaxies, enormously important thing, most massive objects in our galaxy, 10 in the power 15, 10 in the power 14 solar mass, and these are objects which Zwicky discovered the dark matter. And this is our discovery, how we are discovering diffuse objects, and these are clusters of galaxies. And now, after 4 scans of the sky, on the level of 5 sigma, on the half of the sky, we have 23,000 clusters, which nobody observed before. just giant clusters, massive clusters of galaxies up to redshift 2. And they simultaneously are absorbed by people with a Z effect now. And it is very good correspondence. And we can get a lot of beautiful science from this. This is an example. It is comma cluster of galaxies and how one group, galactic group, is going through comma, and we detected, you see, breach, continuum discontinuity, primary shock, secondary shock on the Rosetta images. It is was published in 21, this paper, and I can tell you that it is beautiful. And when I told this to the hydrodynamicists in Russian Academy of Sciences, and they were asking questions, and then they asked me, what is your characteristic time of this process? And characteristic time here is 1 billion year. And they told it is the same as supersonic jet. This motion is supersonic for gas. You know, cluster and group with dark matter is moving, and we see these all shocks and everything with Rosetta. Rosetta is absolutely great instrument. We can go further. I promised you to show you supernova. Nobody saw this supernova remnant in the halo of our galaxy. It is 4 degrees on the sky because it's in very rarefied halo. And it is 3 kiloparsecs from us and 1 kiloparsec above the plane of our galaxy. And we measure now what is the density in the halo, what is the temperature, what is chemical composition of halo around, and from this cluster of galaxies, from this supernova remnant. I can show you only another supernova, and Ildar Habibulin discovered, you see that in the center of this supernova remnant, nobody has seen before. We see L-shell line of iron, which is enormously bright. From the center of supernova, we see emission only of iron. No oxygen, no magnesium, only iron is giving. You know, it is so beautiful and so similar to the predictions of supernova 1A in our galaxy. And now a lot of people are observing this further. We had only 4 scans. Yes, I think I see to the Narek, and many thanks that you were not interrupting me. I have additional 50 slides. This night I was pushing them out. It's 150 papers. 150 papers in the last 4 years. It's an enormous amount of people, at least in Germany, are working. All observatory and its properties are presented in SRG, this paper, review paper in astronomy and astrophysics, published in December of 21. A lot of authors from Russia, Germany, from Russian industry. You can read it, and I can show you, this is me. I also, and this very small proton launcher with special, I don't know how it is in English, but there is additional booster, you know, which delivered this huge observatory, 2,700 kilograms, with unbelievable precision to the L2 point, so that we have fuel for maneuvering and so on for next 7 or 10 years. What will be the political situation? Many of you know that Rosetta is not working. German scientists asked us to switch it off. But this is life when you are doing international collaboration. But launch was beautiful. You see it? It was beautiful and everything was okay. Thank you for your attention. I am glad to speak additional 2 hours.
Thank you very much, Professor Sunai, for this very, very beautiful results and presentations. We have a time for questions.
Splendid. And I think we should even appeal to everyone to make an effort for science to reactivate as soon as possible the observation, because it's a terrible loss, not only for everyone, but especially for science. And I think we should do a document on this. because this is really unacceptable from a scientific point of view. And we have to make a joint voice on this situation. But I have possibly in a few hours a present for you, but I need a data. What is in the in the Fermi bubble, the energy, which you are not the energy, the luminosity that you
Yes,
are
I
observing.
have luminosity. I give you the number, which is under several assumptions. That it is in the galactic center, you understand me?
Yes,
That it is so. I think that number which I have is 10 in power 56 ergs per second.
no, but the luminosity that you have.
10 in power 56, yes. Luminosity is a great subject. If it is, I thought after your questions,
Yes,
if it is, how to say, point source which appeared at some moment and was bright, it might be very bright for short time. You understand me? And in any band, which I don't know which correctly, but under the assumption that this is pumped by continuous years stellar production in vicinity of galactic center.
yes,
Then luminosity is of the order of 10 power 43, 44. You know, this with such things, many explosions and so on, but in general, it is of the order of 10 power 40. It is super Eddington for our black
yes,
hole.
but the luminosity per
Erg
second.
per second. It is 10 power 43, 10 power 42, depending how long is the starburst.
Okay, we
How
will,
long you are producing new stars which then explode.
yes, we are going to see if we can make you a present.
Okay. Oh, present is always good. Okay.
Good.
Thank you. Yes.
Well, thank you very much. We have a time for one question.
Of course, congratulations. But a technical question. You have shown very good reasons for the Lagrangian orbit versus
Great.
the low Earth orbit.
Yeah.
But just as an instrument man, I have to ask you about the drawback. We know that the instrumental background above the belts is somehow higher. So I think that can you compare the instrumental background with the instrumental background of Chandra that somehow could impact on
It is-
sensitivity for very
Yes, I agree
deep
with you.
sources?
It's extremely difficult to compare with Chandra because, for example, up to energy 10 in power, how to say, up to energy 0.7 keV, 0.7 keV. We are not interested in the background at all because we have 1 degree field of view and we have enormous amount of photon from halo of our galaxy, which is nothing for Chandra because Chandra has field of view, you know, of few arc minutes. And we have 1 degree. And it is unbelievable. It's different from. And similarly, we can, I can tell you, there are many things. We are completely different with Chandra. I am, you know, Ricardo was, it's very bad to say that we were friends. He was elder person who advised me a lot in the normal life. When I came first time in America, he organized a meeting in his Institute of Space Science Institute. And when NASA became, pressed me very strongly, and I went, Ricardo came to me and asked Rashid how it is in my peaceful Switzerland. Then he explained how is life, Rashid? How is your life and conversations with NASA in my peaceful Switzerland? Because the meeting was in his institute, Institute of Space Science Telescope, you understand, in Baltimore. And I was only one, and there were a lot of people from Charlie Plenary, Alan Banner, maybe you know, I hope, these people. And they were really pushing me. And when I told Alan Banner was always so nice person. Now without Charlie, I will be just pressed because he's telling ugly things. And He told me every American from childhood knows story about good policemen and bad policemen. They're playing with you this game. Just tell them I can do this, and this, and nothing more, guys. And they immediately agree with you. I returned, you know, remembering every word. My English, as you see, is not very good. Every word of Ricardo, and I just repeated this. And Jerry told, okay, now we understand. We signed the protocol and Moscow agreed and everything was like.
Well, but still now we have to put marketing cooperative.
Oh, yes, we can, but it is, we will discuss. I can tell you only that it is, I learned, there are several people in this room. I learned a lot from people who were doing Yasso Tanaka, Joachim Trumper. We had 4 X-ray spacecraft before. And I am looking at Chinese colleagues who are going through the same way. And I can tell you, it's great to have friends who will advise you that you are not making simple mistake as usual. Usually theoreticians, as a theorist, I always was influenced by theoretical papers, but real experiment, as you, Enrico, know better than other people. Only when really great device, as in your case, is this great polarimeter which you decided. There will be no this great result from polarimetric result from the American and Italian spacecraft, polarization spacecraft, which is absolutely great. I can tell you also that according to our data, we now proved using eROSITA and using your polarization experiment that really hundreds of years ago, there were several explosions in vicinity of center of our galaxy with luminosity of the order of 10 to the power 41 ergs per second during at least 1 year. And we see echo. Understandable what I'm telling you. No, you understand because you are Armenian, American. I am interested for whom English is native. Echo. Okay. It is going shock from this molecular gas is scattering, Thomson scattering X-rays from that explosion. And we were, this was, for me, this was just theory with Ildar Habibulin, you know him. We in Sazonov, we computed this, and Churazov joined us, we computed this, and now we measure it with your polarimeter. And you know how everything will be distributed and where should be the cloud, you know, molecules, how this is going and what should be the polarization degree. And your spacecraft provided us with polarization degree and degree, polarization and polarization angle, exactly what predicted the theory. And it's impressive. Our black hole, which normally has luminosity 10 to the power 33 ergs per second, it's negligible. It's like sun, but in X-rays, it is only 10 to the power 33 ergs per second. For years, there was explosion 100 years ago, 200 years ago, and 400 years ago. 400 years ago, it illuminated giant cluster in Sagittarius B2, maybe you know, 10 to the power 6 solar masses, and X-ray brightness of this scattering of this on this was 20 years. It was very high. And it was decaying more than 20 years. And we saw all this with several spacecraft, including one of the Italian spacecraft, early Italian spacecrafts. It was, you know, X-ray astronomy is a great thing. Then there are people who are doing right instruments. And I am very grateful to a group of Professor Trumper, his pupils, who created eROSITA. It is excellent. Thank you very much.
Well, thank you very much. Let's thank once more the speaker. Okay, now we move to the next speaker. So it's lesson about gravity from black hole imaging. So Rezola Luciano. Okay.
Okay. So, welcome everybody. Today I'll be talking about black holes, and tomorrow I'll be talking about neutron stars, another of my interests. And in particular, I will concentrate on what is it that we have learned in terms of gravity, gravitational physics, from taking photos of supermassive black holes. If we want to study this problem, we have to address a very basic problem, and that is black holes, as you all know, are the most compact objects that we know. Can't make anything smaller than a black hole. At the same time, black holes are at astronomical distances. So naturally, when they are projected on the sky, they are extremely small. But we also have a resolution which is at best 10 microarc seconds. So you have to satisfy both constraints, a finite resolution and a black hole which has to be at the right distance and at the right mass in order to be seen. And when you do this, you realize rather sadly there are just two black holes that you can possibly take a photo of with present resolution. And these are M87 and Sagittarius A star. All the others are a factor 3 or more, too small to be seen given this resolution. And that's what the Event Horizon Telescope collaboration has decided to do. For these two objects, which in principle have the right dimensions, in principle, because we didn't know the mass of M87 star, we wanted to create a virtual radio telescope as big as the whole planet and working at millimeter wavelengths and with microsecond resolution. And I will not go into the detail of how you do this in practice. Okay. Can you move to this next slide? I've lost contact. So in April 2017, so quite a few years back, we have observed M87 for several days, and we produced 4 distinct images. And these are these images over here. As you can see, they are slightly different. They all show this asymmetric ring, and from day to day, they are different, but they are, they maintain a certain stability. And that's exactly what you would expect on these timescales. And the next point, if you can slide, is how do you go from an image, something like that? This is what, as a theorist, I was given by my colleagues. And because I was not involved in the data taking, I was not involved in the image building, which are very complex processes I really do not understand in detail. But I was given this image and I was asked, okay, explain to us why it looks like that and what is it that we can tell in terms of physics. So in order to do this, there are 3 basic steps that we need to do as a theoretician. The first one is perform GRMHD simulations in arbitrary spacetime. Essentially, we need to understand what happens to matter as it moves towards a black hole or something else, which is not a black hole. Once we know what is the dynamics of matter, we need to understand what is the dynamics of light. You have to imagine that as matter falls onto the black hole, will heat up, will interact with magnetic fields, will produce synchrotron radiation, which is what we see. But while doing this, it will do this in a very highly curved space-time, and this requires sophisticated ray tracing techniques in order to obtain an actual image. And the last point, which is not less important, is do essentially what is called image characterization. Take the image and learn from it as much as possible in terms of physics. Okay, so how do you do the first part? How do you do the GRMHD simulations? Well, you have to solve equations. In particular, we have the luxury in the case of supermassive black hole images that the space-time is fixed. This is because the mass in the accretion material is so small compared to the mass of the black hole that you can really consider the black hole metric to be the metric. And so all we need to do in quotes is take covariant derivative over these space-times that we know, Hertz, Schwarzschild, or whatever you want to put in, of energy and momentum conservation, rest mass conservation. Of course, you need an equation of state, but in this case, it's particularly simple. And because you want to do this, taking into account electromagnetic fields, you will need to add the Maxwell equations and the energy momentum tensor that you have appearing on the right, on the top line is of course the composition of all the fields that are present. And these equations are our approximation to reality. Of course, MO87 or Sagittarius are far more complex than this. There are terms which we are not able yet to include, and that will explain some of the reasons why we can't, there are differences in our predictions. At the same time, you need to solve for the light. And essentially, this means solving a Boltzmann equation that tells you about the conservation of the distribution function of photons along the trajectory, the geodesic trajectory that light takes. Imagine you are moving along such a trajectory, you will interact with the matter of the accretion flow. At every point, you will have to ask yourself, am I being absorbed? Am I being emitted? What is my polarization? And again, you have to do this in many different conditions. This pointer is not really working well, but let me give you an example of the first point, okay? How you do this GRMHD simulations. I will give you a very simple reference simulation for a Kerr black hole and an accretion disk. What you do is you start from a torus. Maybe you can move to the next slide. You start from a torus of matter, which is endowed with a magnetic field, and instability will develop. I'm showing you the density here. And in white blue, it's the magnetization, essentially the strength of the magnetic field. You can see the magnetic field is mostly strong near the polar region of the accretion flow. And something else you can also appreciate from these simulations is that accretion is not a steady process. This is because it's the result of an instability, is a stochastic process. It's a bit like when you are next to a waterfall. A waterfall accretion will change with time, although on average will remain the same. And then you can see there are moments where there is a lot of matter being accreted and will compress, and others where there is less. And this is something that will impact the variability of the actual light emitted. This is the inclination at which we think we are seeing M87, and there is going to be a jet coming towards that and a jet moving, receding away from us, which I'm not showing here. And now imagine that you are putting on glasses that are sensitive to millimeter radio emission. That's what you would see. You would see an almost uniform, not quite uniform, ring of light. This ring of light will going to change on time scales of days. And the reason why it looks like a ring of light and not something else is because we are in a very special inclination, as I will explain later on. And if you put in then with the resolution of present observatory, that's what you would expect, okay? So this is a typical flickering of what you would expect from an accretion flow onto a supermassive black hole rotating like a Kerr black hole. And that's what we see. So you can see that there is already a large overlap between what we are able to produce through numerical simulations and the actual observations. Okay, can you move to the next slide, please? So tracing photons near a black hole is not easy. We use lasers all the time, and that's easy for us because lasers on Earth move on straight lines. The curvature on Earth is so little that essentially light moves on straight lines. But if you are thinking about sending a laser beam near a black hole, you would have a very different experience. So just to give you an example, suppose you have a black hole and you have a little thin disk which is emitting light, and you want to take a photo at a given inclination, I. Well, you're going to see first all the photons that come straight from the disk towards you. And this will be the image you will see. And in principle, that's all you see. Just like the only thing you see of myself is my front part of my body. You don't see my back. But in the case of a black hole, you can actually see parts of the disk which are behind the black hole, as you can see over here. And to make things even more interesting, you will see photons. These are indirect image, I-order image of the sheet of accretion which is coming from below. And so you probably have seen this image. This comes from Interstellar. And this explains you why it looks like that. You see the part, unfortunately my pointer doesn't work, but you see the part of the disk which is in front of the spaceship, the part of the disk which is behind the black hole, and the part of the disk which is below. This is a very faithful representation of what happens to light, not quite right. but teaches you a very important lesson. If you have and hide, do not go behind a black hole, will not help. Now, the reason why this is not right is that plasma heats up, and this means the disk will not be thin, but actually be thick, although will be optically thin. So, the kind of disk you have to have in mind is something like this. And I'm taking the same image and I'm just rotating it so that you can appreciate how the image will actually change depending on the inclination. If you are looking at it face on, you will see perfect axis symmetry. The vice versa, every time you are not in this position, you will see, you will first see a dark region, which is the shadow, but you will also see that there is a region which is brighter than the other. And that's inevitable. The reason is that there's always going to be in an accretion flow a part of the disk which is coming towards us and a part which is receding. There's going to be a Doppler effect boosting intensity in our direction. So no matter what, unless you take a black hole which is exactly in the right position, you will always have an asymmetric donut from the image. Now, how do you simulate the spatial parameter? This is really difficult because we don't know what happens near a supermassive black hole. We've never been there. We never have probes that told us what are the physical conditions. So you have to use black holes of different mass and spins, black holes in different theories. You have maybe come up with alternatives to black holes that look like black holes, which either have do not have an horizon or do not have a surface. You also have to worry about the dynamics of the plasma. I've shown you one example of one type of accretion. There are at least two main families of accretion, one which is called sane and the other one is called mad, depending on what is the role played by the magnetic field. And you also have to worry about the dynamics of light, how you produce the light. We said it's synchrotron radiation, but synchrotron radiation, if you remember, depends on the energy of the electrons. We don't know what is the energy distribution of the electrons. So we have to make some guesses and explore different possibilities. So in the case of M87, we started with doing a number of high resolution simulations. About 50% of them were done in Frankfurt. Out of these simulations, for each of these simulations, we built a scenario, which is a situation where you change the distribution of the electrons. And out of this, you build a library. Just to give you an example, this is part of our library, depending on whether the accretion flow is co-rotating or counter-rotating with respect to the black hole, where you make the emission to come mostly from, whether from the jet or from the disk. And as you can imagine, there are many different situations. You can have very small shadows, very large shadows, and so on. And out of this, you build 60,000 images. And then the last part is finding, using algorithms. Mostly these are advanced algorithms like genetic algorithms or MCMC that allow you to go from these 60,000 potential images. These are images which are honest solutions of the equations. They are honest representation of what we understand of physics, but may not be what we observe. And what we get is not a single image. We actually get a distribution of images that match with a given degree what we are expecting. And this is an example. On the left, you have the observations. On the right, you have one theoretical model. We know everything about the model on the right. So you may think that you know everything on the model on the left, but that's wrong. That's because there are many theoretical models that equally well match the observations. And I'll give you an example here. So these are, at the bottom, there are 3 different images which are matching the observations with the same degree. You can have a number of different metrics in which you can measure this. And on the top, there are the equivalent simulations. And the one in the center is a Schwarzschild black hole, so non-rotating black hole. The one on the right is a Kerr black hole, rapidly spinning. The one on the left is also a Kerr black hole, but counter-rotating. So depending on this degree of freedom, where you put the electrons, you can get exactly the same image. And, from a physical point of view, this is good because it gives us certainty, robustness of the results, because all of the images that we produce are black holes and produce that image. on the other hand, is bad because we are blind to one of the most important properties of black holes, its spin, at least with these resolutions. What is it? What is the difference with respect to Sagittarius A star? So there are some disadvantages and some advantages when looking at Sagittarius A star. Overall, I can tell you Sagittarius A star is far more difficult to model. The first one is that there is interstellar scattering, which distorts the images. There is something between us and the center of the galaxy, which is intrinsically scattering radio photons. We don't know where this scattering happens. It could be near the black hole. It could be near us. It could be anywhere. It could be a single screen. It could be a distribution of electrons. We don't really know. All we know is it's there and disturbs us. This is rather natural. If you think of M87, we were just looking outside of the galactic plane. Here we're looking right in the middle of the galactic plane. The real killer is the variability. If you take the typical timescale to go on an ISCO near a black hole, which has the mass of Sagittarius A star, you find out that this is of the order of few minutes. And we're taking observations over a timescale of 8 hours. So we're taking photos over 8 hours of an object which is intrinsically changing every 5-10 minutes. You can imagine this is going to introduce a number of difficulties, and it is one of the reasons some of the techniques we've used for Sagittarius A star were rather different from the one we used in M87. M87 is about a day. You look at it for 8 hours, it's not going to change much. Can change from day to day, as I've shown you, but not over the single day. And then, of course, just like for M87, we don't have, in jargon, a full UV coverage. We just have a small portion of the information we would like to have in order to have a sharp image. So these are the two black holes. They are in real size, so next to each other. And you can see that essentially there are about 30 images which are compatible with M87. In the case of Sagittarius A star, there are 9,000 images which are compatible. We know the mass in the case of Sagittarius as well extremely well. It's 4 million solar masses. In the case of M87, it's 6.5 billion solar masses. And as I explained, the variability is very different. It's amazing how they are almost the same size. This is something we didn't know. We didn't know the mass of M87. There were 2 guesses for the masses, but if it happened that the mass was a factor 2 smaller than what we have measured, which was one of the predictions, we would not have been able to do any image because it would have been too small to resolve. So let me come now to the real topic of my presentation, which is gravity. So how do you put this into a gravitational context? Okay. Can you move on? Okay, here. So everything is in this dm. Okay, let me explain what dm is. There is this, my pointer again doesn't work. There is this calibration factor alpha c. This is a number which comes from, which contains all the information we can put about the errors in our measurement. And then there is the next important point is this delta. Delta measures the deviation away from the expected shadow angular size in the case of a Schwarzschild black hole. Okay, so it's 6 square root of 3, or what you would expect for Schwarzschild. So delta measures our deviations away from not general relativity, but from a Schwarzschild black hole. Delta equals 0 is a Schwarzschild black hole. And what we do is, again, our analysis doesn't give a single value of delta, gives us a distribution of delta. And this is shown over here in the horizontal axis versus the normalized probability. The blue stripe is what we know from general relativity. In the case of a Schwarzschild black hole, delta is equal to 0. In the case of a Kerr black hole, it will be less than 0 because shadows in Kerr are smaller. And depending on the spin of Kerr, you will have smaller and smaller delta. So that's why we have this blue stripe. And as you can see, out of the comparison, the comparison is perfectly compatible with what I would expect. Shown also with a green line is the case for M87 star. Okay, so what this tells us is Well, there is a large uncertainty, but everything fits perfectly with the idea that we have GR. I find this is a beautiful plot. This is showing black holes over 8 orders of magnitude. So these are, again, the deviation in delta as measured from Sagittarius A star, from M87, and those are the same uncertainties that you get from gravitational waves from LIGO. Now, you may think, how? Well, LIGO doesn't take images. Well, LIGO takes ring downs. Ring downs are produced near the light ring by the effective potential there. So effectively, you can map the uncertainty in the ring down in an uncertainty in the location of the light ring. And that allows you to have plots of this type. Once again, the horizontal stripe is GR. And everything over 8 orders of magnitude is consistent with GR. So, one could say, well, that's it, job done. Let's just go and have some vacation. Actually, if you open the archive every day on GRQC, you will find that 3/4 of the papers are not about general relativity, about alternative theories of gravity. So how do you test gravity? Well, the fact that general relativity works well is reassuring for all of us, but there are other options, and other option may be better. So you want to, if you think a little bit about this is our blessing and curse for us who are doing astrophysics, okay? In astrophysics, we will just receive images or, electromagnetic radiation, gravitational radiation, and our job is to interpret these messengers. But there are many different ways in which you can interpret that message. And so there are degenerate explanations that are possible. And so, testing theories of gravity is actually really, really hard. There are 2 approaches, one which is an agnostic approach, which I will explain, and another one which is much harder is an agnostic approach, where you try to concentrate on specific example and you try to convince yourself whether or not this is ruled out or compatible. So let me start with the agnostic approach, because this is something that I worked and I feel is the right approach. So as I explained, in this business, we don't need the field equations. All we need is a metric in a given coordinate system. So let me call it G mu nu of X alpha. And you can think of writing this metric in some kind of an expansion where you have additional parameters, let me call them AI and BI, such that in the case in which they are 0, you end up with well-known solutions in general relativity. These expansions are known as RZ or KRZ, and there are 2 mathematical tricks which make them very, very powerful. The first one is that we use a coordinate compactification. So rather than studying space-time from, say, 2m to spatial infinity, we compactify everything to be between 0 and 1. 0 as the horizon, 1 is spatial infinity. The second is we use a Padé expansion near the event horizon, because metric functions will change very rapidly there, may have coordinate singularity. But if you have a Padé expansion which is built to handle poles, you have the chances of having a very nice representation of any metric you want. So the idea is then, whatever metric you can come up with, in whatever theory you can come up with, in whatever method you can come up with, be it analytical or numerical, you can map it into a KRZ metric. All you need, because of these properties, are 2-3 coefficients to get sub% precision, okay? So we played with this, and the idea in this approach is that you don't make an observation and say this is a Kerr black hole. You say we made an observation and this is a black hole which has these parameters, A1 equal blah blah, A2 equal blah blah, and then with time you will find out what are the actual values of these parameters. In the other way, in this gnostic approach to alternatives, what we have considered is, well, let's suppose we are considering a dilaton black hole. How does this change? What about if you have a boson star? What if you have a reflecting hard surface like a Grava star? How would an image from a Grava star look like? What if you in general consider black holes which have charges, not electrical charges, but just, hairs? I don't have time to go through all of them. I will just go over a few of them. Let me just start from a dilaton black hole. So this is a dilaton black hole inspired from string theory. We consider the simplest case where there is just one additional hair, which is a scalar hair, the dilaton field. And because we have built a machinery that does all of what I've shown you, simulations, ray tracing, and so on, we have done the same, but over this space-time. And you have Kerr on the left, you have dilaton on the right. Well, you look at these movies. By the way, you have to match the two somehow. In this case, we match them to have the same ISCO. Okay? In this respect, the actual size of the event horizon would be different. You know, it's like comparing apples and oranges. At least some quantity of these two have to be the same. Here we said that the ISCO is the same, but the same conclusion comes if you consider different matching. You look at these movies and you say, okay, actually, I can tell the difference. But the point is that you're not going to be looking at movies. All you have are images. And so what you have to do is compare images, and that's what you have. These are the images for a Kerr black hole and a dilaton black hole. And yeah, if you would shuffle them for me, I would not be able to tell which one is which. If you put in scattering in, it's even harder. So the bottom line is that it's very hard, given the resolution we have now, given static images, to tell black holes from different theories. Most of the theories will produce black holes which are perfectly compatible with what we see. Of course, then one has to justify why looking at dilaton black hole, but that's a different discussion altogether. Well, what about boson stars? Boson stars are great objects, okay? You start putting in a scalar field. We expect scalar field to be present in nature. Boson stars are natural explanation for dark matter in galaxies. So what happens if you have a boson star? Now, a boson star is, you have to imagine, is this fluffy boson condensate, which has infinite extension, but very compact core, almost a black hole compactness. So you have to imagine that there is a boson star, and now there is a torus of matter inside this boson star, and you just let the simulation and the MHD do its job. And what happens is that, well, two things happen. First of all, there is no event horizon, so matter will not be absorbed. We'll just move in towards the center of this boson star, but it will not reach the center of the boson star. The reason being there is a centrifugal potential. Because there is no absorbing surface, the potential will be like a Newtonian potential, will be like 1/r². So matter that goes very close at one point will saturate near a certain region, which you can determine on the basis of the magnetic field, and then try to move outwards in the vertical direction. So a boson star would look like that, would have not a shadow, would have an inner region which is populated by light. There is a region which is empty of matter because of this potential, but this will not be comparable with a shadow. So this is what I'm trying to say. This is the result of the imaging. As you can see, the shadow is much smaller in this case. And if you deconvolve with the precision of our instruments, you see that the shadow in the bottom part is much smaller than in the top part. Now, in principle, you could say, well, I can change the shadow in the bottom part by, for instance, increasing the mass of the boson star. Yes, you can do that. If you increase the mass of the boson star, the shadow would increase, but not, then you would break the constraints on the mass. So given the mass constraints that we have, what we've seen is not a boson star. But it's good that at least we can distinguish boson star from black holes. So I will try to wrap up. Let's consider different black holes. At the end of the day, we have a measurement on the size of the shadow plus a certain error. And we can ask, well, does the shadow of any black hole with any other charge fit in this? This is shown in this region over here. So this is a bit of a complicated plot. On the left, in the wide region, I'm showing you the allowed size in the shadow. Obviously, the dotted line is Schwarzschild, and the uncertainty is given by the uncertainty in our measurement. And what I'm showing on the horizontal axis is the normalized charge. That is, the additional hair will change the shadow, and I'm writing everything into a normalized manner between 0 and 1, so all the charges are written in that way. And anything that moves out of this white region is excluded. And as you can see, this is what I was already telling you, it's very hard to tell different black holes apart. Most of the black holes, even with the largest possible charges, are within the allowed region. It's really very exotic objects, naked singularities, Kerr-Newman with very large charges that do not fit this picture. But it's a principle that is useful. Now we have a way of having a constraint on possible values, and as technology and our ability to make these observations will improve, this white line will become thinner and thinner. And at one point, you will be left with very little alternative choices. This is the same when you put in also the joint observations from Sagittarius A star. You can see that the uncertainty goes down, not a lot, but that's the trend. So let me come to the conclusions. I think I've explained that imaging, taking pictures of black holes is a complex science, requires a lot of expertise. I don't have them all. Data taking, imaging, building, and then theoretical interpretation. Over the last 5 years, we've done more simulations of accretion on two Kepler black holes than we've done over the previous 30 years. That's because we had very clear goal in mind. And we're starting to look at alternatives to black holes, alternatives to black holes in general relativity. What we know is other black holes are very hard to tell apart. Boson stars are easy to tell apart. Naked singularities are also easy to tell apart. Now, if you ask what is it that EHT has given to science, well, it has shown that at least in 2 galaxies, there are supermassive black holes. You just have to extrapolate this to the 10 to the 11 galaxies that we know, and you see the impact of this. Really, from a theoretical point of view, my point of view, the importance of the EHT has been that of transforming the event horizon from a concept to an actual testable object. And if you think this is the most important result, because we've gone from, writing theories about event horizon to actually making the event horizon something we can measure with precision, and this is the way to do science. Thank you.
Thank you. Well, thank you very much for this talk. Unfortunately, we are having many things, and we have now a very urgent presentation also. We are late, but we had a splendid presentation from Rashid. On the other point, you went before to another meeting, but you missed this meeting. And I think many of the considerations you have presented, we have some thought about. And tomorrow, for example, there will be a talk given by Reinhard Genzel. And there are doubts about the black hole in Sagittarius A. There are doubts. But there are also certainty. And one of the certainty is that the angular momentum is not there. Therefore, all this beautiful thing, fortunately, you are here for a few days, and therefore we will have time to speak. But also, I would like to tell you that we have obtained a very interesting result, how to proceed to study black holes. And we have made a one-page document, which I will give you. And I was doubtful till a few minutes ago, because my talk on Monday, Penrose was present. at a distance. I just received an email from him, which is quite interesting. And he points out that the electrodynamical part is quite important, and that we have introduced a new concept, old, 50 years ago, that you cannot treat a Kerr black hole without considering the irreducible mass. I will give you a small page to look at, and then tomorrow we will discuss. Thank you anyway for the interesting talk.
Okay, yep.
Let's
Thank you.
go quickly to the next talk. No, we have excuse me? Okay, Mr. Chairman, something has to be done here, and okay.
We have the right now.
Yes, we postponed it.
Okay, we are sorry, there is a change, so we postpone the next talk to after the coffee break. So let's have the coffee break short, like 20 minutes coffee break, and we come back in 20 minutes sharp, and we start the session again. So then, okay, everyone, please take the seats. So we start the second part of the morning session.
How to make it work?
One. Okay, everyone, welcome back. So let's start the session. So our next presentation is the Einstein probe mission by Professor Yuan Weimin. So please start the presentation.
Good morning, everyone. I would like to thank the organizers for the invitation for this plenary talk. I'm going to talk about a new mission, which is called the Einstein probe, which is designed to explore the dynamic X-ray universe. I'm Weimin Yuan from National Astronomical Observatory of the Chinese Academy of Sciences, and I'm talking on behalf of the whole Einstein probe consortium. So the Einstein probe is a mission led by Chinese Academy of Sciences and participated by ESA, MPE, and CNES. So actually today I'm wearing a t-shirt of the ESA Einstein probe team. I started with this X-ray image taken by MAXI, which is on the International Space Station. So MAXI scans the whole sky every 1.5 hours in the X-ray band. As you can see many X-ray sources. And as we know that the X-ray sky is full of variable sources and transients. For example, this is a very well-known X-ray black hole binary, thickness X1, it varies a lot. And there are AGNs of supermassive black holes. They also show strong variability over time scale of hours to years. There are sometimes transients as well in the X-ray sky, like this X-ray novae. It's a low mass X-ray binary. It was discovered during an outburst by many orders of magnitudes in X-ray. And also we have transients like the brightest ones, the gamma ray bursts. So the X-ray sky is pervaded by various types of transients and variable sources. And there is a very rich history in X-ray and also gamma ray wide field monitoring of the sky. Here I plotted the missions starting from the early days of the X-ray astronomy and versus the areas of the X-ray detectors. Actually, what you can see is that as time goes by, the detectors is becoming larger and larger in order to detect fainter and fainter objects. But because of the sensitivity, the limitation of the sensitivity, so most of the galactic transients are X-ray binaries, and the X-ray galactic transients are mostly gamma ray burst. And in order to detect the bulk of the extragalactic X-ray transients, we really need to build a much larger X-ray detector to go to detect the phantom objects, or we need some new technology. And I have to say that in the past of years, all these wide field X-ray and gamma ray detectors are built from the non-focusing technology. For example, pinhole or coated mask. And most of these detectors were built to observe the universe in the hard X-ray band or even the gamma ray band. And so far, there's no dedicated transient science-driven missions built so far. And I have to say that until recently, there has been very little contribution from China, but China is starting to make contributions. So we have a GCAM, which is a gamma ray. Okay, thank you. I think its battery dies out. Okay, so we have the Einstein probe mission. We launched this mission in January this year. So you can see that for Einstein probe, the area of the detector is about 700 square centimeter. It's not terribly large compared to Sweet Bat and Swarm and Maxi, but we can go to the higher sensitivity. We were able to detect the extragalactic X-ray transients because we are using a new detection technology, which I'm going to show you on the next slide. Before that, I would like to mention a few new high energy transient and science drivers to build a new mission. You have heard about this, tidal disruption, events by black holes, and gamma ray burst in the high red shifts, supernova shock breakout, electromagnetic wave counterparts of gravitational wave events, as well as counterparts of neutrino events, and other very interesting things like the quasi-periodic eruptions in X-ray band and so on. So all these new high energy transients require the next generation of high energy or X-ray monitors, which can look deeper and further, and also to monitor the sky at a higher cadence. So now we have the technology to do this. Okay, this is called the lobster eye optics for X-ray focusing imaging. As I just mentioned on my first slide, that most of the previous conventional wide field X-ray monitors were built from the non-focusing techniques, the coated mask or slit camera. But now we have this technology to do X-ray focusing imaging for wide field of view. And this is called the lobster eye micropole optics, okay? So the principle is that we know that X-ray can be focused by grazing instance reflection. So for trials of the reflection, we can focus imaging, focus X-ray and get imaging. So this is this principle, how the eyes of lobster work. So different from the eyes of a human being and most of the animals. So the light is focused not by refraction, like our eyes, but by reflection for the eyes of lobster. It's very strange. So in 1979, American astronomer Roger Angel proposed this idea to build a wide field X-ray monitor, mimic the imaging principle of the eyes of a lobster. So this is the eyes of lobster. There are many holes, square holes. So the square holes are perpendicular to the surface. The surface is actually not a plate. A surface is actually a part of a sphere. So this is a micropole optical plant we're using to build the telescope. You can see there are many small holes or squares, which is very small. The size is about 20 or 40 micron. So on one of these plates, which is about 4 centimeter by 4 centimeter, there are about 1 million such holes. So the X-ray photons can be reflected on the walls of these holes. So for one reflection, Okay, for one fraction, you follow these blue lines, it forms a straight line. If the light is reflected by the orthogonal walls of these pores, then the image can be formed another horizontal line. But if a photon is reflected twice on both the orthogonal walls of the pores, then it can be brought onto the focal spot in the center. So this forms a very characteristic point spread function with a central focal spot here, and also Trucy just like that. So now at the laboratory, we can reach a point spread function of the core, which is about 5 arc-minute, 4 with Arc maximum. And for this kind of grazing instance reflection by the micropole optics, it's very different from the conventional X-ray telescope like the Water 1 type, which has an axisymmetric configuration. For such kind of optics, there is no major optical axis, as you can see. So any direction is identical to the other one. So which means that for sources from any of the directions, so they can form an image on the focal surface in the same way. So this is the reason why such optics can be built into a wide field of view monitor, and there is almost no vignetting effect. And it is also a true focusing imaging, unlike the coated mask. So since 2010, Professor Shuanan Zhang from IHAP, who gave a talk yesterday, he built a laboratory at X-ray imaging laboratory at our Institute, National Astronomical Observatory of the CAS, and we started the lobster eye technology, the R&D. So this is an X-ray image we obtained at our laboratory. We developed this technology and built a prototype for the Einstein probe. We called it the pathfinder of the Einstein probe. Actually, this is the one of the Einstein probe wide field X-ray telescope. It's a qualification model. And we launched it 2 years ago in China aboard a technology demonstration satellite. So this is the first light of this experiment 2 years ago, looking at the center of our galaxy. And you can see that with only one module, we can reach a field of view of 340 square degree with a 800 second exposure. There are more than 10 X-ray binaries could be detected. So for comparison, this is the size of the full moon. So imagine this is focusing imaging X-ray telescope with a very large field of view. And so we published a paper in APGL 2 years ago. And for the Einstein probe, we have 12 of such modules. So to give you an idea of the focusing capability, so I show you one of the LIAR experiments. So LIAR detected an outburst of a neutron star X-ray binary. This source, there was no detection here, and the source became brighter. So this is the image. At the same time, MAXI on board this International Space Station also detected this outburst. So this is a comparison of the point spread function of MAXI, which is this circle, compared to the LIAR. So you can see LIAR has really very good spatial resolution, hence the very good sensitivity. And LIAR is a prototype of the Einstein probe wide field X-ray telescope. So for Einstein probe, we have a very similar or even better imaging quality. This is monitoring of the LMC with LIAR. So this is the MMC in optical and LMC in X-ray by our LIAR telescope. You can see the movie over a period of several years. So we detected the light curve of LMC X1, X2, X3, X4. You can see that a giant flare was detected for LMC X4. Okay, so Einstein probe is a time domain astronomical mission. The goal is to discover soft X-ray transients, and also monitor source variability with improved sensitivity. So sensitivity is about 1 to 2 orders magnitude deeper compared to the current wide field monitors like Swift BAT or Maxi. And we would like to characterize the transients and also variable sources by a very quick X-ray follow-up on board. And also we like to disseminate the transient alerts to the whole astronomical community in time. So this is the milestone. So the mission concept was proposed in 2012. Adoption happened in 2017. We are lucky to have ESA and MP on board in 2018. So they are part of the consortium. And the CNAS in France also joined 2 years ago. We launched the Pathfinder 2 years ago, Leia. And the launch of the Einstein probe happened early in January this year. The lifetime is for 3 years and the goal is for 5 years. So this is overall view of the satellite and also the payload. So there are 2 telescopes. One is the wide field X-ray telescope. We call it WST. So it's mainly developed by the CAS, and the ESA contributed in testing some of the device and also one of the flight modules and one qualification modules as well. So it is made of this lobust eye micropole optics, or with a CMOS as X-ray sensors. It's got a very large field of view. It's 3,600 square degree, which is 1.1 steradian. It's working in the soft X-ray band from open 5 to 4 or 5 keV with a very good angular resolution of 5.5 minutes. It can reach a sensitivity of 1 millicrab at an exposure time of 1 kiloseconds. So there are the 12 modules surrounding the middle. There are 2 identical units of follow-up X-ray telescope. We call them FST. So this is a collaboration between China, ESA, and MPE. So they are the conventional one type optics with PNCCD with 1 field of view, a field of view of 1 telescope is 1 degree. So the 2 units are co-aligned looking at the same direction. So the effective area is 300 square centimeter at 1 keV for 1 unit. So basically this is the same design as ISO-theta. So we can say that we have actually 2/7 of the ISO-theta satellite. The spacecraft was developed in China. It's got the capability to do onboard data processing very quickly. And once the transient is found, so the telescope, the spacecraft will slew and point the FST to the newly discovered transients to start observations immediately. So we have also very quick data telemetry. I should have to say that we use the BeiDou, the Chinese satellite navigation system, BeiDou, a short message system, we can downlink and uplink comments very quickly. And also we use the VHF network from the French CNAS, which is developed for the SWAN mission. So this is the wide field X-ray telescope. I don't have the time to go into details. So it's one module. We have 12 of this. We have to say that in total, we have 422 micropole optics placed and 48 CMOS sensors. So this is 1,700 square centimeter. This is perhaps the largest detector array for focusing X-ray telescopes built ever. This is follow-up X-ray telescope FST. It is a joint effort developed at IHAP CAS, participated by ESA and MPE. So you can see this, they are identicals to one of the ISO-theta telescope. So the satellite, so it looks like lotus flowers. Okay, so you see the flower petals. It's quite a huge one. So its weight, the weight is almost 1.5 ton, and the dimension is 3.5, almost 3.4 meters high. It's quite a large one. So this is how it looks, the payloads. Okay, so the Einstein probe was launched at Xichang Flight Center by a Long March 2C rocket in January online this year. So this has been a long time since we had this idea and also developed the technology. I show this a movie about 10 minutes after the liftoff, the separation of the spacecraft and the rocket. So you can see now the last scene, the last view of the spacecraft. So the height of the orbit is nearly 600 kilometers. Okay, I'd like to show you some of the first lights we achieved in April this year. This is the first light of the Wide Field X-ray Telescope, WST. This is Cas A supernova remnants. This one, because it's a very nice cross with a central spot. And also we can get the X-ray spectra at the same time. Papis A, sorry, this is Vela supernova. It's a Papis A, it's a Vela supernova remnants. You can see this is only one of the CMOS sensors. We have 14 of them. So one CMOS sensor can cover the entire Vela, which is 9 degree by 9 degrees. So the wide field of view can be demonstrated here. And also the lobster eye MPO technology can also imaging diffuse emission, not only point light source, but also diffuse emission. So this is the entire field of view of WST looking at the galactic center. So you can see that this is the galactic center region scope X1. So its cross represents is the image of an X-ray binary, and you can see also the diffuse X-ray emission. So the total 48 CMOS sensors. Okay, so this is the real image, the first light image of WST. If you put this field of view on the background of the whole sky, you can see that it's really huge field of view, okay? This is one snapshot, only one snapshot. So it covers 1/11 of the solid angle of the entire sky. So we only look at the anti-solar direction. So in 3 orbits, which is 5 hours, we cover the entire night sky. So on each day, any direction of this anti-solar direction can be sampled several times, maybe 6 or 5 times. Okay, so this is the first light of the FXT. We observe the Crab Nebula, so you can see the pulsar wind nebula here. And also we have a very good observing mode is timing mode. With this timing mode, the time resolution is 42 microseconds. You can see this Crab Nebula, the Crab pulsar, the spin period of which is almost 34 milliseconds. We can clearly resolve this spin period. Another first light image of FST, this Papis A supernova remnants. So you can see the central compact objects. It's not as fantastic as the Chandra image, but reminding that this is only for follow-up X-ray observations. It's very good already. So this is X-ray spectrum. You can see many lines. Okay, in the following minutes, I would like to say a few words about the preliminary detection scientific results. So this is a new mission. We are still analyzing the data. We just completed the commissioning phase and actually start the nominal operations from yesterday. So I don't have many scientific results to present to you today, as Professor Sanyayev presented for his data. Maybe in the future we can do this. But I'd like to present you some very preliminary results. So this is gamma ray burst we detected, not by Einstein probe, but by the Pathfinder layer. So what I can say, because I don't have much time, all I can say is we observed this GRB. It's the second brightest GRB ever detected in history. We observed this jointly with GCAM, also one of the gamma ray burst detectors of the CAS. What I can say is that we can say the hard X-ray and the gamma rays, we think they are powered by relativistic jets of GRB, but the soft X-rays detected by Leia is very much likely powered by a magneta emerging from a burst at the onset. And this is also consistent with the association of a kilonova signature found by JWST. So in the past half a year, during the commissioning and calibration phase, the WST has detected nearly 4,000 X-ray sources. So this is a distribution of this nearly 4,000 X-ray sources over the sky. Though they are mostly AGNs, X-ray stars and stellar flares, and all sorts of, all types of X-ray sources. And we have detected more than 30 X-ray transients in the X-ray band with high signal-to-noise ratio, and more than 100 transients with at a lower signal-to-noise ratio. And for this high signal-to-noise ratio transient, we have released more than 40, I think 50 ATEL or CCN already. The stellar flares also detected. The number is something like more than 300 so far. So I'd like to show you, this is the very first X-ray transient discovered by EPWST on February 19th during a calibration using the crab. This is a crab labular. So you can see a transient started, appeared here, and after 200 seconds disappeared. This is a light curve, and it's very much likely an X-ray rich gamma ray burst. Okay. So I show you here examples of light curves in the soft X-ray band detected by the wide field X-ray telescope on EP. By fast transients, I mean they appeared and lasted for about hundreds or 1,000 seconds and disappeared completely. I would like to mention that only 1/3 of these transients have hard X-ray or gamma ray counterparts as GRBs. And for the rest of the 2/3, we completely have no idea what they are. They might also be gamma ray bursts, which are rich in X-rays, but maybe something else as well, maybe supernova remnants, sorry, supernova shock breakouts. This is one of the example of gamma ray burst, which has the redshift measurements. This is the very first EP gamma ray transient, which has redshift measurements. It happens to be at a redshift of almost 5. Thank you. Almost 5. So this may indicate that the Einstein probe may have the potential to detect high redshift GRBs. The idea is simple because for high redshift GRBs, the bulk of the X-ray or gamma ray photons are redshifted to a lower energy. So they may have a lot of energy in the soft X-ray band in the observer's frame. And also Einstein probe has got this improved sensitivity by more than 1 order of magnitude over Swift band, for example. So it's not very surprising if we detect more gamma ray bursts at high redshifts. And also another interesting feature I would like to draw your attention is that the light curves detected in the soft X-ray band is very much different from the conventional gamma ray and hard X-ray light curves of GRBs. As for this one, the green curves, the green lines represent the light curves detected by Einstein probe. It's lasted over 1,000 seconds. But on the other hand, the gamma ray and hard X-ray light curve is just 1 point, lasting less than 50 seconds. There is a marked difference between the soft X-ray light curve and the hard X-ray light curve. So it's hard to define when the GRB occurs, okay? So I guess there are some interesting new physics inside. And if we put this source at a distance of a redshift of 7.5, it still can be detected by Einstein probe WST. So this WST has the capability to detect high redshift GRBs. And so we also detect some interesting galactic transients. I listed 3 here. So one of these is classified as a magnetic CV. And one is, actually, I have no idea. So we have no idea what it is. And for this one, we don't know what it is. So, and in May, we detected outburst in the SMC. So you can see the light curve and also the X-ray image. And the X-ray photons are all in the soft X-ray band. There's no photons built beyond 2 keV. So it's likely a BE binary system with a white dwarf. And also we have achieved the onboard trigger for FST follow-up automatically. So the trigger after 1 minute after trigger, FXT started observations. So this is the first realization of this automatic follow-up observations of FXT following a trigger on board. So it turned out to be a stellar flares. We can monitor known X-ray sources. I give you just examples of a long-term light curve. We start to build up the long-term light curves of these sources. Okay, my conclusion. So the Einstein probe is a space X-ray observatory to explore the dynamic X-ray universe. So since launch on January 9th, the performance verifications and calibration observations have completed. And the spacecraft and the instruments are working fine. We have detected more than 30 X-ray transients, and the nominal science operations just started actually yesterday. So Einstein probe is a newcomer with great scientific potential in time domain X-ray astronomy. Here I listed the website of the CAS website, also ESA website for Einstein probe. And thank you very much for your attention.
Well, thank you very much for this very beautiful presentation. So we have time for questions.
Well, just statement. We are celebrating today for the starting operation of this beautiful satellite. And we have been following every day the preceding result in the calibration phase and so forth. And we look even more now for the definite value for the years to come. And thank you very much for doing this beautiful telescope. But apart from that, let's see if there are questions.
There are short questions because we are running.
Quick one, congratulations. For the EP detection of that high redshift gamma bursts, the redshift determined by the X-ray detection itself or by other complementary
observations? Yeah, we have to use optical telescope, very large. So that redshift was measured by VLT.
Okay, thank you.
Okay, let's thank once more the speaker. So then we move to the next speaker, which is fresh results and surprises from James Webb Space Telescope. So Adriano Fontana.
So good morning, everybody. First of all, let me thank Remo for inviting me to this conference. I apologize, Remo, for being not here the first 2 days. Now, I will try to drive you through some of the results of James Webb. I'm sure you have heard so many things about it that you're already very familiar with it. So let me just put it in context for a second. You know, James Webb is an infrared telescope. And this, I compare the size of Webb with other instruments. So you may immediately see this is essentially a telescope as big as those we have on the ground today that is brought on L2 and observed in the near infrared, and is significantly larger than Hubble and Spitzer. My point here is that it is usually believed to be the successor of Hubble. And so it's a big leap from Hubble, but actually this is an infrared telescope. And so it's actually the successor of Spitzer, which was an infrared telescope observing at the same wavelength. And so you may see there is an early factor of 10 increase in the collecting, in the radius of the telescope with additional improved technology, of course, from at the same wavelength. So we really, it's one of the biggest advances especially in this in wavelength range. And now images can tell you much more than 1,000 words. So this is the very first image taken by Webb. I'm sure many of you have already seen it, and compared with the same image observed previously with Spitzer. And so you may immediately see that you have an incredible amount in the spatial resolution. So you see all these points, how smaller they are. And this comes from the fact that the full width, as you know, scales with the diameter, with the inverse of the diameter. And you see an incredible amount of objects that were impossible to see in Spitzer. And again, this comes from the fact that for a number of reasons, the signal to noise increases, in this case, at least as the square of the diameter. So there is an enormous increase in sensitivity and spatial resolution. Just for the spatial, for the sensitivity, James Webb is from 100 to 2,000 times more efficient than any other instruments from ground or space that we ever used. So the expectations from these instruments were really impressive. Now, I will concentrate most of my talk on the very early universe and high redshift galaxies. But before these, let me give you a hint of a couple of results. I'm sure you have seen on the media so many announcements. So there are a couple of things that are really interesting to see. One is, of course, exoplanets. Webb is really revolutionizing this field. And the idea here is that when you have a planet transiting in front of a star in the Milky Way, not only you see the decrease in the flux because the planet transits, which is obvious, but most importantly, you can see the differences in the spectrum of the star due to the atmosphere, which is a thin shell around the planet. So of course, you need a very precise and stable telescope to do this kind of job. One of the very exciting results of the last year is about this planet. There is a new class of planets, it's so-called Lycian, which are water planets larger than the Earth, but smaller than Neptune. And these planets are covered mostly covered or entirely covered by a water ocean. They have an hydrogen-rich atmosphere. Their conditions thermodynamically are similar to Earth. They are inside the habitable zone. And so in principle, they are suitable for life development, the kind of things we see in sci-fi movies so far. Now, the spectrum observed in this very planet by James Webb reveals, you have to go to the infrared and you see all the bands due to the different molecules. And this is the first time we detect methane and carbon dioxide in an object, in a planet, which could, in principle, which is in the habitable zone. The tantalizing thing is that they also detect this molecule, DMS, which is on the Earth, is produced only by plankton in the ocean. So you have a planet which is surrounded by a big ocean, and we may have detected a molecule which is on the Earth is produced only by plankton in the ocean. So this is tantalizing, just to show how difficult is this game. These are the real data, the real spectrum. And you have to fit the very complex molecules with a combination of different molecules, of course, studying in a complex model, which includes also the radiation from the star, blah, blah. So it's fairly non-obvious. And the signal is this small difference here that you see. So it's the signal of this DMS is still very weak, and so the detection is considered very tentative at the moment. So maybe will be disputed by future observations which are going on this summer. But I mean, it's an idea of what this telescope can do. The other thing of course, is just an excuse to show this very nice image you have all seen. But is to tell you that this is not about only images, but you can do real science with images. So if you zoom inside this area, for instance, you see, if it goes on, yes, you see that these shapes here, these things here are cocoon due to the emission to the jet originated by this bright newborn star, which is inside here, and you have a jet in this direction, which impacts on the surrounding area. So these things are being used. There is another nice image here. So the study of jet is very important also to understand the emission mechanism of this jet. For instance, in this case, it has been found is surprisingly dominated by cold molecular gas and not ionized one, as expected. So even the physical mechanism that drive this emission of jet is significantly being affected by new results from James Webb. So this is just a few nice images, but can give you an idea of how many scientific revolutions maybe can be originated by this telescope. Now let's move to my preferred topic, which is the birth of galaxies. This was, again, one of the main motivation for building these telescopes, because galaxies become, of course, much fainter and redshifted when you go to very high redshift. So they move to the infrared. And so there is an industry started from the data from the Hubble Deep Field and so forth, which study the evolution of galaxies as a function of redshift. This is often summarized in this very popular plot, which you may be familiar with. The usual form, which is in the upper right, is the amount of stars formed every year in the universe as a function of the time from the Big Bang. In the upper one, you see the popular way, the normal way, which is in log scale as a function of redshift. But in linear units, what you see is actually here, there is a phase around redshift after 4 giga-year from the Big Bang, where the stuff emission activity was at its peak. And we also see, of course, a morphological transformation of galaxies. Today, we have the big giant galaxies, but when we go back in time, we see smaller and smaller objects down to the hybrid, which were existing at very early time. Now, the key point is that this diagram does not reach 0. So it does not reach the epoch of Big Bang or close to the Big Bang or the very first galaxy. So we cannot, with previous observations, we were not able to go very close to the Big Bang or in the real epoch of formation of the very first stars. Now, there are, of course, it's important because we are exploring the universe, but there are a number of physical good reasons to go to even higher redshift. And I remind you that the physical conditions at the time were completely different. So the universe was much denser, was very low was very metal poor or even primordial. The CMB was warmer, and so the basic temperature of the gas was higher than today. There was no ultraviolet background, and the density fluctuation were much smaller than today. So we enter in a completely different regime of physical conditions that require some way a different kind of physical models, if not a new physics. In addition to this, this is an epoch where we may see evidence of a new physics of some kind. So there are a number of papers. Every day there is something. So, but just to give you an idea of what can be done, for instance, people have ideas, and I will come back on this, on the possibility of primordial black holes, non-stellar origin. And if you have a population of primordial black holes here on the left, you may have additional seeds which help forming stars. And so the Maddow-Dickinson plot, so the stuff emission rate, may be higher at high redshift compared to what I simply expected extrapolating the low redshift evolution, because you have additional seeds. When you let time pass, then this effect disappears because galaxies grow enough that they don't care about primordial black holes orbiting around. Completely different approach, you may have early dark energy or different non-standard models, non-standard lambda CDM models. And in this case, you have, for instance, in early dark energy, you have additional power in the power spectrum. So you have more halos of a given mass at a given time. And so you may be forming more galaxies. So keep in mind these two options, because they all go into the direction of having more galaxies at very early times. And again, this is an effect that you can see at redshift 8, but essentially disappears at lower redshift. Other examples on the other side, you may put limits on the possible mass of a work dark matter particle by looking at the very number of galaxies. You cannot have too many galaxies if you have a work dark matter particle. So there are a number of limits, and the UV luminosity function, which are the green points, give you limits which are entirely reasonable, entirely consistent with other kind of astrophysical constraints. And finally, again, from the very pure number of galaxies, in this case of massive galaxies, you can have even limits with some assumption on the cosmological parameters for quintessence models and similar kind of models. So there are a number of reasons for what happens in the very high redshift universe can help us revealing evidence of new physics. But before we are certain of these, of course, we have to be sure that the baryonic physics is completely understood and under control, which is, of course, is not as today. Now, the situation before James Webb was difficult in the sense that we had a physical wall at redshift 10. This is the redshift distribution before James Webb. So you see there was essentially nothing beyond 10. And the reason is fairly obvious. When you have a spectrum of a galaxy, which is in red on the left, as you move in redshift from, say, 7 to 8 to 9, it moves redder and redder. And at some point, you get out of the HST wavelengths. And so essentially, you don't detect anymore, or you detect in one band, and you don't know what you're looking at. So there was this hard limit needed to go to the infrared. Spitzer, as I mentioned, was not sensitive enough at all. And so you need James Webb to go into this regime. So because of these, the first data that were coming were really highly expected. And in particular, we have been lucky enough to be leading the very first deep field obtained with James Webb in the context of the GLASS survey. And when we received the data on July 16, when the very first data of James Webb were released, we immediately went looking for data and for these kind of objects in the deep field. And we immediately identified two very clear and convincing candidates, one at redshift 10.6 and one at redshift 12.2, which were so-called photometric redshifts, so were candidate at these redshifts. Now, the surprising thing is that based on every evolution you may guess, and I will come back on this, of our previous data, in the data we were expecting exactly 0.1 candidates. So honestly, we were relaxed. We said, okay, we will find nothing. We have already prepared a nice paper saying, sorry, we found nothing, but there is a good reason for this. And we actually saw these two guys in the data. And of course, the statistics was not great, but anyway, they were so interesting that we decided to rush and write a paper. And we actually came to the archive after only 1 week. And these two objects, since the data were public, were also observed by another group, also detected by another group. And we have the two papers submitted on AstroPH with a difference of 3 minutes. So this can give you an idea of the pressure. So, and this was 1 week after the date, it's submitted on 19 July and we got the data on 14 July. So in 5 days, both teams rushed like hell and produced these two papers, fortunately saying exactly the same thing, that we found these two galaxies and which were not expected. Now, this was not a random fluctuation. So now the situation is much clearer. We have thousands of candidates beyond redshift 5 and hundreds beyond redshift 7. And it's now very clear that the number of galaxies is in excess of any prediction which were based on theoretical models or on the extrapolation of data from HST surveys. So just as an example, on the left, you see the luminosity function, the number of galaxies as a function of the magnitude. And the number, especially beyond redshift 10, for instance, you may see the purple plot around redshift 14 are much larger than the extrapolations before. So there is much more, the evolution of galaxies before redshift 10 is much accelerated compared to what we were expecting. So objects are either brighter or more massive or both, and we don't know. So you may wonder, well, these are candidates. There is no spectroscopic redshift. Here instead comes the power of James Webb. The second surprise, well, it's not really a surprise, but we were expecting, but it's been a shock anyway to see how easy it is to get spectra of galaxies at redshift 10. So there are plenty of galaxies now at with spectroscopic redshift 10. Sometimes you see emission lines, as you see over there on the top left. Sometimes you just see the hydrogen break here, which is another very unique feature. So the current record holder are these two galaxies published by Stefano Carniani a few days ago. The highest redshift one is 14.32, and as you may see, the spectrum is also very clear and incredible higher signal to noise. So the key point here is not only it's easy, but it's so easy that we can now be sure that the fraction of the objects that we have identified in the images are for the vast majority indeed at high redshift. So it is confirmed that the number of galaxies at high redshift beyond redshift 10 is much larger than expected. Now, the questions why this is happening, well, there are zillions of ideas, of course, about why this happened. I will not go through the details, but essentially there are a number of motivations and explanations due to baryon physics. So of course you may claim, say, the IMF was different. So let me say, one class of categories say, okay, objects are not more active or more massive, but are brighter. For instance, you may have zero metallicity stars are very bright. IMF, top heavy IMF is very bright. So this brightens the objects, although they do not form faster than expected. They are just brighter than what we expected. Another class of ideas is that no, they are actually forming faster for a number of reasons related to the star formation efficiency or for the star formation stochasticity. And the jury is still out about these options. There is another completely different category, which is, of course, is the AGN. So we may have more AGN than expected, which brightens these objects in the center. And again, keep in mind these two options for the following. So to understand these things, what can you do? Well, you have to go and look at the spectra and understand what are the physical properties of these objects. So if you look at the average spectrum, which is something you may do now, you may stack hundreds, as you may see, 500 of sources beyond redshift 5. There is an evolution which is expected. Is an exercise I did with Guido Roberts Borzani, and you see galaxies become slightly less metal rich. They have more, the ionization of the gas is increasing and their stellar age are decreasing. So this is what you expect from the global population. Again, you see a mild evolution, so you don't see anything dramatic happening when you move to a high redshift. Again, because the evolution is milder than what we expect. So it's important to go and look at individual objects. And here comes the first big surprise. There have been identified a number of faint AGNs inside these galaxies. So there are a number of objects. When you do the spectrum in the detail, you see that there are clear evidence of wide lines, broad lines in excess of the expected width for a stellar population. And this comes in galaxies, as you may see, at redshift 8 and 6, but even at redshift 10, when there are other indicators based on different things, including the X-ray detection, and even at redshift 10.6, where there is this GNZ11 object, which has a number of high ionization lines, which are typically produced only in AGNs. So we don't have a good statistics yet. We cannot say the fraction of AGN is this, but it's very clear that there is of the order of 10% of the galaxies that we see, the bright galaxies at high redshift, have a central AGN. And the stellar mass of these AGNs is of the order, is estimated, if the scaling relation still holds, of the order of 10 to the 6. Now, 10 to the 6 is not a big number in the local universe. Maybe Luciano disagrees, but is a huge number at high redshift. So look at the rightmost plot here. This is a theoretical prediction. So this is a plot of the mass of the black hole as a function of the redshift from the Big Bang to now. And of course, black holes have to increase over time. So to reach 10 to the 6 at redshift 10.6, as in the case of GNZ11, so to reach this point, you have two options. Either you grow from a stellar black hole to super Eddington rate all the time, continuously, or you start from a primordial massive black hole of the order of 10 to the 3, 10 to the 4, and follow a more natural Eddington increase. So the evidence that there are a number of black holes of this mass at those early times is lending some support to the idea that there are primordial black holes of the order of 10 to the 4 or so in the early universe. Again, the jury is still out, but is an interesting indication. So surprises are not over. When you look at individual objects, you see that there are objects where have a low metallicity, but the metal abundance of the individual elements is different, is significantly different from the average. So in particular, there are objects which are enriched in nitrogen. So the hydrogen, as you may see, that peak is very overabundant. Now, this is interesting because on the local universe, this overabundance of nitrogen is found in the globular cluster. So there is, again, a tantalizing suggestion that for these objects, which are particularly bright, we may be seeing a phase where the globular clusters are being formed, or populations consistent with the epoch of globular clusters formation are formed. I find these results spectacular in the same line. This, thanks to gravitational lensing in a cluster, this object on the left is actually stretched due to the gravitational lensing, and when you reconstruct the source, the image on the source plane, you see that this galaxy, which would have looked point-like otherwise, is actually made of star clusters, of small star clusters of the order of 10 to the 5 solar masses. So again, most of the formation of stars in this kind of things, these kind of galaxies, is concentrated in star cluster, in very small bound region, very dense. We may be seeing the formation of a massive globular cluster, or in any case of objects that therefore thereafter they diffuse in the stellar medium of the galaxy. Again, let me come back to another surprising result. We have come back, you remember the two very bright galaxies that we identified in the very first data. The highest redshift one, G8Z2, we came back and observed it spectroscopically, and not only we confirmed that it is indeed a redshift 12.3 as expected. What is spectacular here is that we have both the near spec data and the MIRI data in the relatively far infrared with the detection of H alpha. So we are detecting, just to give you an idea of the power of the instrument, we can detect H alpha to a redshift 12. Which is really unbelievable. The key point is that these objects, which again is one of the very bright and unexpected objects, is full of these emission lines, has a strong carbon-4 emission line. When I first saw the spectra, I said, well, okay, that's an AGN with that carbon-4. Unfortunately, we did the analysis in the detail, and the presence of an AGN, unfortunately, is uncertain based on this data. We need better data to clarify the topic. But again, gives you an idea of how unique are these objects. So it's very low in metallicity. It's very ionized. Departs from any local relation you may think about. And again, it's another object which is nitrogen enhanced. And so maybe again, an object that we see when it's forming a population similar to globular clusters. So for those of you who are not excited, I remind you that by the detection of H alpha, let me just remind you that when I entered in this game nearly 30 years ago, this was the name of the game. So as a function, the redshift as a function of magnitude, we were limited to magnitude K21 and redshift essentially 1.6. So nowadays, I put a star there, but actually the point is outside of the screen because we really progressed incredibly. And if you believe this is because I'm old, these are the same data. We observed the same object with VLT. We wasted 30 hours of VLT looking at this object and found essentially is exactly 0. So because the object is simply too faint, even with those emission lines, we have not been able to detect at this rate. So again, it's interesting to see that if you look these two objects that I discussed, GZ11 and GH2, are the brightest at very high redshift, and both of them are in a phase with very high ionization state, low metallicity, and supersolar nitrogen. So again, we may be seeing a very peculiar phase. May I have 2 last minutes? Okay, final question is about reionization. Now, you know what the story is. We believe that the universe was, of course, it was neutral after the Big Bang, and then at some point, the first sources started to ionize, first of all, the bubbles, the region around them. So they formed the bubbles around the various objects, which eventually coalesced and formed a globally ionized intergalactic medium. This phase is called reionization. It's stretched between redshift, say, 10 and 6 based on our data. Now, to compute out the mathematics implied in this business implies a number of numbers. You need to know the number of galaxies, how many galaxies did the job, what was their UV emission, and because you need UV photons to ionize the medium, and what fraction of these photons were able to escape from the galaxy, because we know in local galaxies, UV photons don't escape from local galaxies. And so these 3 numbers are captured. They depend on the UV luminosity density. First, the second is a number which is a spectral shape, which is called Xion, and the third is a fraction, which is the escape fraction. And there is a 4th number, which is the clumping factor, which is also unknown. So the problem is all these 3 numbers, the number of galaxies, their UV luminosity, and their escape fraction are all difficult to measure. However, we can do reasonable estimates with James Webb, based on the data with James Webb. And the key conclusion is that we have found too many galaxies with too much ionizing power and too much escape fraction. If we take the formal numbers that we get from James Webb for these 3 things, we get an efficiency in the reionization of the universe that essentially violates the constraints that we have from the Planck mission, from the optical depth of the CMB, and also predict a reionization history of the universe, which is this one in blue. So the ionized fraction as a function of redshift, which is much anticipated compared to anything we have estimated and measured so far. So so there is something we still don't understand about how reionization proceeded. And on top of this, we have also AGNs. So we may be in tension with everything we understood before. So I conclude with the take-home messages that we can now easily access the galaxy population up to redshift 4, and galaxies evolved lower compared to what we were expecting, and there were an abundant fraction of AGNs. More interestingly, I believe we have, I hope we do, a number of problems still to address. So why there were so many galaxies? What was the history of star formation rate? Which are the seeds that originated the black holes? Were they primordial black holes? We still don't know what happened at redshift beyond 14 and which sources reionized the universe. So I'm pretty sure we'll have plenty of questions to address for the next meetings. Thank you.
Now it's working.
Several of these James Webb galaxies with surprising rates of growth and quenching also, namely impeding the continuous formation of stars, are observed also with ALMA. And the observations with ALMA show that the content of gas, neutral gas in these galaxies must be extremely large, sometimes being even more than 50% of the overall mass of the galaxies. Do you think these very high densities revealed by ALMA could explain the surprising accelerated evolution of these galaxies?
So it's difficult to say in the sense that so we're looking at slightly different redshifts, first of all, okay? So the quiescent galaxies that you mentioned are, as say, somewhat lower redshift of the order of 5 or so. So it is difficult to say because, I mean, these kind of objects that we see are predicted to have a very efficient feedback. So you have a high ionization, you have a lot of probably very massive stars. They explode like supernovae as hell. So we expect they to have a significant feedback, and so to expel the gas at least from the center of the galaxy. So it would be surprising, but I mean, we'll see. I think I know for sure people are using ALMA to estimate, to measure the gas there and see. There is another question there, maybe. There is a question there.
There are a lot of questions, but I think we are running out of the time. Very quick question, just one very quick.
Okay, could you mention the difference in number predicted by lambda CDM structure formation at high redshift compare with your data, the number or estimate? Thank you.
No, so there are papers doing this exercise. The key point is that, again, it depends. So when you have the hollow mass function, when you compute how many, then you have to convert into a number of galaxies. And for these, you have to assume an efficiency of conversion, which is unknown. Okay, so that's the problem. So it depends on the assumption that you do. We are still in the range that the efficiency, that the numbers can be matched by tuning the efficiency, but maybe not. So I think it's too early to say at this level.
Sorry, we are running out of the time. Maybe we can continue the questions during the lunch break. Sure. No? Let's thank again the speaker, and we move to so we move the next presentation with Professor Ruffini and Wang Yu. So the most energetic binary driven hypernova 1. Start.
Well, we come in. We continue this very exciting meeting. I promise a surprise for Rashid. We will do that at the end of the talk. And let's start. The talk I can introduce, then you continue, and then I conclude. Is that okay? How do you work with this? Okay. We already presented these 3 sources, which are the most powerful GRB which have been observed up to now. And I started with the crab at the beginning. I remember when we introduced the black hole with John Wheeler long ago, and this now has become, thanks to the work of Roy Kerr, which has given us a metric to work with, and especially to the collaboration with Christodoulou and Hawking, we were able to find, finally, the basic equations governing the black hole mass energy formula. It's better that everybody, I think that no paper on black hole rotating Kerr or Kerr-Newman can avoid to take this equation into account. The mass is known in function of 3 parameters: the mass, the angular momentum, and the irreducible mass. But there is also, in the case of black holes which are not in isolation, but in presence of a magnetic field, there is also a new concept, which is the effective charge. Of course, the irreducible mass is essential because it characterizes the two basic quantity of black hole physics: how much energy is extractable from a black hole. And this is the formula, m minus m irreducible, and how much mass is extracted. And that depends if the transformation are reversible or irreversible. But the table, the new table, has been presented in this meeting on Monday, thanks to collaboration also with ORG. Let's go on quickly. Okay, this you know, Beppo-Sachs, the first identification of a GRB, our model of BDHN as binary of a CO core plus a neutron star around, and explosion creating accretion, and then accretion creating a fast spinning neutron star and a black hole. All this is now standard. We have many publications, but we have also a first definite result. The first one was 1901-14C, in which we have evidenced that they are in a GRV 7 different episodes. And these 7 episodes, which were announced in 2023, now have become a reality. The first episode, which is the most unexpected one, has been the supernova, which triggers all the process and is trigger the process of gravitational collapse, generating the spinning neutron star and the black hole. And then, of course, the fundamental process has been how to extract the rotational energy of a black hole by electrodynamic process, and that is well known and now is published, and then you can see all the details, and some further details are coming up. What I want to present and then go fast, and then maybe I ask Wang Yu. The first very interesting thing of this new very big event has been that we predicted the presence of a supernova ashes due to nickel decay in this source. And this was our prediction and in a GCN, and now this has become a reality in James Webb. Why this is very exciting to bring back to the everyday life, this process is the one which generated the material which we found on the euro. But apart from that, let's go seriously, like everything else, to these 3 sources. You come in. And in these 3 sources, we have, as you can see, 1, 2, 3, 4, 5, 6, 7, the 7 episodes characterizing the GRB. And this has been done thanks to the work with Wang Yu, Liang Li, and of course all the other people in the group, and especially Rueda.
Okay, so let me complement the details of Professor Ruffini's figure. Luciano, can you show my slides? Oh, I'm the person who gave the talk on artificial intelligence on Monday's plenary. Yeah. No, for sure. No, now I'm talking about the figure. The procedure of the binary driven hypernova. A moment. No, I sent you by email.
Episode, okay, here first at all the gamma ray bursts have to be normalized properly and expressed in the units. First at all, not everybody described GRB with the rest frame in second and the luminosity in erg per second, and this with all the different wavelength and so forth. Okay.
Okay, they are looking for my slides. But first, I think let's explain more on this figure, the simulation.
Yes.
Yeah, with the collaboration of Chris Fryer, who received the medal yesterday. So initially we have two stars. So on the left side, it is a very massive carbon oxygen core of about 8 solar masses. And on the right side, it's a companion neutron star about 2 solar masses. So at a given moment, this massive CO core collapses to a supernova, and its eject expands outward. So at here showed 40-second, we can see the expanding ejector just reach the companion neutron star and the accretion starts. The accretion rate can be very high, up to in the order of 10 to minus 2 solar mass per second. And at the time of the second figure, 100 second, we see that the accretion almost forms an accretion disk. And the turbulent, and this companion neutron star also turbulate the density profile. And it pulls back, look at the third figure, some material to the original now it's a new neutron star because after the collapse of a supernova, we have a new neutron star at the light blue point there. Therefore, in this system, the accretion will continue on 2 neutron stars, the new one and the companion older one. So if the accretion rate is high, it depends on the distance between 2 stars. That companion one, so the right side one, will reach the critical mass of the black hole, and then it collapses to a black hole. And also you can see, because we have this turbulence, so we will have a lot of material around these 2 compact stars. So we will have the continual fallback accretion for many years, perhaps. Luciano, my slides is okay? And okay, good. Not this one.
No. What is it?
And the bottom figure and the upper figure are 2 views from different direction. The upper one is from the top, so we can see the equatorial plane. And the bottom one is from the side.
There is a problem.
A problem of my slides.
Okay, let's go back to my talk. No. My talk.
Okay, so
let's go back to my talk, and then you described. Okay, this I did. Okay, what happens? No, it's okay. We will solve another day. Okay, let's go back here. Okay, this is 220101. We understand all the details. In the first second, actually of the order of 3 seconds, you have the collapse of the core. then you have the fission process, and then you have what Wang Yu was saying, the accretion of the supernova onto the neutron star binary companion, creating the black hole, the red one, and that is the MEV emission. And below, you have, as soon as the black hole is formed, you have the JEV emission here represented, and at the same time, you have the formation of the afterglow here, and of the optical emission from the new neutron star, the pulsar, which has been just starting at a millisecond period around 10 seconds. Okay, we understand this. You will have all time to have all the details. The only thing we are insisting that this is not an exception, it's a rule, this GRB structure. And in particular, we find exactly the same structure with the supernova rise lasting of the order of few seconds and collapsing, creating the gamma ray burst. And then soon after, also in this very, very powerful source of 160625b, you have this marvelous result that you can reproduce again the Fermi GBM emission due at the moment of formation neutron star, but also you find the surprising result that there is an, that there is this component at the beginning, a very high energy emission from the black hole, very high energy emission in the during the formation of the black hole in the Fermi-LAT and Fermi GBM, but there is also this very significant emission in the red. This is the novelty, which has been observed in the early part of the afterglow. We have seen this again in 160625b, this signature, and this was one of the most important features discovered by Lipунov. But what is extremely beautiful is that also when you go to 221009, that feature in red, which is just coinciding with the Fermi GBM data and the formation of the black hole, the second component, which is just due to the accretion on the new neutron star, that red part is also present in this source and is practically the same slope as the previous one and corresponding to the TEV emission. This is just to show the redundance of three different sources, and this one is by far the most energetic one. I discussed already the problem of 1901-14C. I will not repeat this here, but I would like to ask Wang Yu to describe these last slides. Can you do that? We took now one of these GRB 220101, this one, which we understand very well, and what we did, Wang Yu, what you did this morning.
Like some minutes ago, Professor asked me to extrapolate the light curve of the afterglow.
For you, Rashid.
Yeah.
This is for you.
Professor, yeah. to extrapolate it to 50,000 years later. That's the radius of the Fermi bubble, about half of our galaxy size, to check the luminosity. So converting to the second, it will be like a 1 point some times 10 to 12 second. So this is one very energetic B, and it has a very high luminous X-ray afterglow. So at that time, the luminous, if it follows the power law all the time, so after 50,000 years, the luminosity will become in the order of 10 to 38 erg per second. So if we take more GRBs, this range can change, like from 10 to 53, 10, 50, or 10 to 35 to 10 to 40 perhaps, like 5 order of magnitudes. So,
But if you assume this, which is one of the most powerful, then the luminosity if you assume that there was a GRB at the center of the galaxy, like this one, you end up with a luminosity observable on Earth of the order of 10 to the 38 ergs, which is the order of magnitude which you observe in the Fermi bubble. I'm sorry to, this will deserve an entire, we will discuss further, but I ask Wang Yu to check right away, and therefore the GRB not only not only they are by themselves very energetic and very important, but they can also be the source we discussed on Monday and of the crab event, but also they could be the source, like Rashid was mentioning. They have been activity in the galactic center in the last 200 years, 2000 years. Okay, there was this activity even earlier. And this is the result. If you extrapolate the GRB of data energy at the galactic center, this will give today the observed Fermi-Lat observation, the Fermi bubble observation. You see what, okay?
Yes, may I ask your colleague, could you explain us your writing about luminosity in erg per second? At which frequencies or at which energies this radiation is going? Every moment, shifting at every moment, is it shifting or it is on given frequency? For example, if this is optical emission, how it evolves, and could you explain us?
Yes,
which radiation you are speaking?
Here on the plot, we show the majority radiation is in the X-ray.
In the X-ray and also in the JEV.
Yeah, also in the JEV, because this is a very broad band from the radio, optical, X-ray to MEV, JEV. But MEV a little, usually, mostly are in the X-ray.
Yes.
But this system can evolve. We have the energy source of it. The energy output is first from the fallback accretion, but I don't know if it can last so long time. But second is from the neutron star. The neutron star has a spin down energy. So how to convert the energy to radiation is another problem. You can have a very long time Fermi acceleration, so the particles can be at a very high velocity, then you can have higher energy.
Acceleration is much faster. It's also possible.
Yeah, sure.
But this is just to take a GRB which we completely understand from the nearby one and put at the galactic center and extrapolate. Of course, the emission is just the emission of the original machine, which is emitting the JEV and the X-ray in the rest frame. And then you just let that radiation propagate, and this is the result. Anyway, Yes.
Integrated the whole energy output from all these 50,000 years.
Yes, it's very trivial.
Was
It's,
released.
Yes, it's trivial. If you integrate the total energy, now we understand things so well that we can go back to this and tell you the total energy was 3.5 10 to the 54 erg. Because we assume that GRB nearby, assuming that it was long ago in the galactic center. It's very simple. I mean, once that you understand the gamma ray burst, you can apply over and over. The important point is to understand the gamma ray burst, and we understand that all gamma ray bursts have 7 episodes. And this episode, they just reproduce in all different wavelengths and all different processes in all of them. In the most powerful one, of course, they are GRB very soft, and they are a family of BDHN. BDHN 1 around 10 to the 54, then you have the less energetic and so forth. We are speaking about the most powerful one. The 3 most powerful one that we know up to now, but I think this is enough for just to let you know, and everybody know. We will have all time to go through the details.
Very impressive.
Excuse me?
This is very impressive energy release because this energy is practically maybe 3 solar masses.
Yes, but
in MC square.
Yes, but we have understood this. It's just the rotational energy. All this talk is, all this meeting is about that. The rotational energy, I gave you even the table. From now on, that is the table to consider.
Okay, but it's good to read paper.
Yes.
Okay. Okay.
Okay, thank you very much. Let's thank the speakers. Okay, very good. Then we move to the next presentation is repeating transients from center of galaxies extreme mass ratio binaries. Professor Pasham. I will notify you when there is 5 minutes left. Yeah, perfect. Yes, start.
Does this work? Yeah, it's fine. All right, great. Good afternoon, everyone, and thanks for being here. Special thanks to Professor Ruffini for inviting me, but also some of the team members to this conference. So yeah, in my talk today, I will tell you about a mysterious new class of repeating soft X-ray transients people have been uncovering in the last 5 years or so. And I'm going to present the case that perhaps these repeating transients represent a population of extreme mass ratio binaries. So, like I said, the work I'm going to show you today is done in collaboration with several people, some of whom are present here. Petra, Francesco organized a special session yesterday, and there's Michael. And sorry, you need to refresh. You need to, excuse me, IT. You need to close it and refresh it because I've updated the slides. Sorry. You just click refresh now. So anyhow, yeah. So yeah, if you see any of these people, they'd be interested to chat with you. Cool. So, yeah. So the outline for today's talk is as follows. First, I'm going to give you the scientific motivation to study these kind of extreme mass ratio binaries. Then I'll show you observations, and I'll give you a very high-level overview of these observations. There's many subtle details that I'm not going to go through, but I'll be happy to talk to you about it. And then I'm going to summarize some other models that people have proposed for these repeating transients. And then, assuming that these are extreme mass ratio binaries, I will give you examples of potential detectability with future space-based missions like LISA and TAIGI. And then finally, I'll tell you something about the prospects of improving the sample size of these systems. Right now, we are at a very early stage. We only have about a dozen systems. And again, this whole field started only a few years ago. So science modification. So we've all seen pretty pictures from JWST before, but unfortunately in my talk, these are the only pretty pictures. But what I want to highlight here is that we now know that pretty much all galaxies contain supermassive black holes. But what's becoming increasingly clear is that a large fraction of galaxies also contain these dense collection of stars close to the centers of these galaxies. These we now know are nuclear star clusters. They have collection of stars, old, young, and also stellar remnants. When people do this more systematically, what they have found is that more than 60% of all galaxies contain this dense collection of stellar objects very close to the massive black hole at the center. And this dense collection of stellar objects includes regular stars and also degenerate objects like white dwarfs, neutron stars, stellar mass black holes, and even perhaps intermediate mass black holes. So theorists have proposed various mechanisms to bring these objects close to the supermassive black hole and form some sort of a binary in a tight orbit, perhaps in a configuration similar to here. I'm not going to go into the details of every single mechanism that has been proposed. If you're interested, you can look at these references. But the main point is there are ways in which you can form an extreme mass ratio binary, which in the context of today's talk means a massive black hole with a companion, where the companion can be a star or a compact object. Cool. So why are these kind of systems interesting? If the companion is also a compact object, then for a certain range of mass ratios, certain range of periods, these should also be detectable in gravitational waves in the future with LISA and TAIGI. And that obviously is an exciting prospect. Imagine living in a time when, unlike LIGO, where you see transient events, you would see electromagnetic trains, periodic signals in the X-rays, and simultaneously you would see gravitational wave trains coming along as well. And that would be really an amazing era to live in, and that would help us address several fundamental questions in physics. For example, dark energy. So there was a parallel session yesterday about the Hubble tension. So dark energy, as probably already know, constitutes roughly 70% of the energy content of the universe. We don't know much about it, but what we do know is that it's responsible for the acceleration of the universe. The best way to probe the acceleration of the universe is by measuring the Hubble constant. But apparently, people in cosmology are having trouble figuring out the value of the Hubble constant in the local universe. Depending on what method you use, what probes you use, either you use probes in the late universe, this marker is not too good. Okay, anyhow, late universe or early time universe, the value you infer for the Hubble constant can be quite different. The tension between these methods are anywhere from 4 sigma to 6.5 sigma, or 6.2 sigma. So when you have a problem like this, what you need to solve this is systems where you can measure Hubble constant to better than 1% accuracy. And if you have systems, multiple systems emitting both gravitational waves and also electromagnetic radiation, you get the redshift from EM, electromagnetic spectra. And from the gravitational waves, you can get the luminosity distance, and that would help us pin down very precisely the Hubble constant, which has already been demonstrated with the binary neutron star GW170817 just in one case. And other things you can do is imagine having the wave trains X-ray band and also in the gravitational wave band. Then according to this paper, you can actually sort of match them up and figure out the relative speed between gravitons and light to an accuracy of 10 to the minus 17. So that would be a completely new regime in which you would probe gravity. From an astrophysical perspective, one of the big questions in supermassive black hole community is what is the evolutionary history of supermassive black holes? How did they grow over the age of the universe? And spin distribution of supermassive black holes will exactly tell us how they grew over the age of the universe. Right now, we do not have an unbiased measurement of the spin distribution of supermassive black holes. So here I'm showing you example distributions from 3 different scenarios in which supermassive black holes grow. If they grew by mergers all the way from high redshift to low redshift, that's the distribution on the left side. If they grew by steady accretion, they tend to spin up. So most black holes should be fast spinning. If they grew by chaotic accretion, then they tend to be low spinning. So having both gravitational waves and electromagnetic information, we'll be able to break down this mass spin degeneracy, which we have in the electromagnetic community, and pin down the spins of supermassive black holes, and ultimately answer this question of how supermassive black holes grow over the age of the universe. Now, if the companion happens to be a star instead of a compact object, then we would have several systems like our own Sagittarius A star, where we'll be able to track orbits of stars at a level of many, many, many more orbits than what we can do with Sagittarius A stars. The tightest orbit for Sagittarius A star is something like 16 years, the S02 star. But as I will show you some systems that we have, they are only a few hours. So you can sample many, many, many orbits of this companion. Cool. Yeah, so the big question is, can we identify such binaries with the technology that we have now? Can we identify things with this kind of a geometrical setting? So that brings us to the observations. We have identified, we've identified different flavors of repeating transients in the last couple of years. And depending on how they manifest in the data, they're called quasi-periodic oscillations or quasi-periodic eruptions or quasi-periodic outflows. And hopefully it'll become clear in a couple of slides why we call it that way. So I'm just going to give you an example of what I mean by these 3 different flavors. So quasi-periodic oscillations are these highly stable, soft X-ray modulations that people have detected in a small sample of systems that look like this. So you have on the y-axis the X-ray brightness or the count rate, and the x-axis is time. This particular system, you can see there's beautiful modulations happening on a time scale of an hour. And there are a few other systems that we've detected. One's 2 minutes, the other one's 3.5 hours. Here's an example of what I mean by a quasi-periodic eruption. So as you can see here, the modulation, the X-ray brightness is more abrupt, more like an eruption rather than a smooth oscillation. So that's why they're called quasi-periodic eruptions. And finally, the most recent phenomenon that we've identified are quasi-periodic outflows. And what I mean by that is there's a narrow band in the X-ray spectrum, which is dominated by an ultra-fast outflow. And if you track the strength of that outflow as a function of time, it shows these kind of modulations. This particular system repeats every 8.5 days. So cool. So hopefully you all now understand what I mean by repeating transients, what flavors they come in. The other really interesting thing that has come about just in the last couple of months is that these repeating transients appear to be coming after a huge outburst happens. And this huge outburst perhaps is from a stellar tidal disruption event. So just quickly, what is a TDE or tidal disruption event? When you have a star coming too close to a massive black hole, the tidal shear across the length of the star can exceed self-gravity of the star. That's when the star gets disrupted. Roughly half the material falls back onto the black hole, and that can create a huge outburst, detectable either in X-rays or optically. So what we have found in the last couple of months, years, is that all these modulations that I just talked about are detected months to years after this huge outburst happens. So here's an example of assassin 14-like, a tidal disruption event, one of the best studied tidal disruption events. On the y-axis, I'm showing you the X-ray luminosity. X-axis is time. Notice the scale here. The time is hundreds of days. And X1 through X5 and C1 are deep Chandra and XM Newton observations. When you look at those data and take a power density spectrum, this is what you see. You see this beautiful 2-minute quasi-periodic signal. If it were completely periodic, you would have the entire signal be in one bin. The fact that it's spread out in multiple frequency bins means it's quasi-periodic, not strictly periodic. And this happens a few months after the TDE happens. This is another TDE that was discovered by a ZTF all-sky survey from the ground in 2019. And these are the optical light curves of that TDE. On the y-axis is the magnitude, x-axis is time, a few hundred or a few months at a time. And at the time it was discovered, it was completely normal. There was nothing out of the ordinary for this tidal disruption event. We looked at it with NICER. It was not detected, pretty much flat non-detections. We looked at it recently, 4 years after the tidal disruption event happens, and this is what we see. Beautiful bursts separated by roughly 2 days. So that establishes that these QPEs are connected to tidal disruption events. Now, this third phenomenon, quasi-periodic outflows, again, the same thing. The blue is the optical outburst. And then a couple of months later, the X-rays start to rise. When you look into the details of the X-rays, there is an outflow. You track the strength of the outflow, and it shows this kind of behavior, repeating behavior, roughly every 8.5 days or so. So just to give some numbers for theorists in the audience, the amount of kinetic power in each of these ejections, so roughly happening every 8.5 days, is on the order of 10 to the 43 ergs per second. So now that I've told you, all these repeating signals are detected after some sort of a huge outburst happens in the optical. So how does that fit into the picture of orbiting objects? So the basic idea is as follows. You have 2 objects going around each other. That's this plot here. And this happens in vacuum. So you don't detect anything from them. A third object comes along, a star. It gets tidally disrupted by the massive black hole. And that creates a huge amount of gas surrounding the supermassive black hole. However, at this point, the new accretion flow is too bright to see the second object. At some point, the accretion flow settles down into maybe a steady disk, and that is when this object interacts with this disk and produces these repeating signals. That's one of the ideas. And we have support for this idea, at least in 2 systems. The amplitude of these quasi-periodic eruptions tend to be going down with time, which you expect in the scenario that I just described. Cool. So I've told you they're connected with tidal disruption events. Another thing that we have started to discover are these outflows from all these systems, and the quasi-periodic oscillation systems, quasi-periodic eruption systems, and obviously in the quasi-periodic outflow systems. Here's just a quick overview of an example. So in the left side, in the top panels, I'm always showing you a spectrum. And the bottom panels, I'm showing you the ratio of the best fit continuum model divided by the data. So you see these kind of features here. There's like a feature dip here, dip there, dip there. And those can be modeled with outflows that are moving at roughly 10 to 20% the speed of light. And these outflows are not always present. They happen during a certain phase of these modulations. Like, for example, in some systems, they happen during the rise. In some systems, they happen during the decay. So they come and go. So one of the ideas that has been put forward for these outflows is by Petra, where what I'm going to show you here is a GR-MHD simulation done in 3D. On the left side is a side view. The right side is the top view. You have a binary. The secondary object is going around the primary massive black hole. There is an accretion disk. And what the secondary is doing is every time it punches through the disk, it drags the material from the disk and pushes it towards the magnetic poles. And because of the magnetic field there, it is launched along the poles. So if you happen to be aligned with the polar region of the system, you will see these ejections coming your way on the time scale of the orbital period of the secondary. Can we go to the next? Yeah. So you may be wondering, if it's an orbit, it should be strictly periodic. But that is not true. If it's an orbit, there's GR effects that make the system very highly quasi-periodic. So here's an example of a system spinning black hole with a test particle going around it. And on the right side is just a representation of the nature of how the burst should be. This is, again, not done with any real physics, but it's just like a point source going around, hitting the disk. It's the times of the interaction of the disk. So as you can see, it can be highly chaotic because of GR effects, like precession of the disk, but also precession of the orbit of the secondary as well. So cool. So far, I've kind of discussed a lot of these things in the context of extreme mass ratio binaries. But again, I want to stress that this is by no means the only model. And there are many models that have been proposed for these kind of systems. And they can be put into two categories. One's with objects going around. And even in that kind of framework, there's many flavors of how you can produce the radiation. So these are all the models with objects going around. On the left side, there's also other models which do not involve any orbiting objects, but some sort of an inner disk accretion physics that is new. So cool. So now, under the assumption that some of these are extreme mass ratio in spirals, I will show you the detectability prospects with LISA. So this is work done by a student, Shubham Kejriwal. So the basic idea is he took a sample of extreme mass ratio in spirals from published literature, and he asked the question, what is the time scale of such MREs now for them to be detectable with LISA in 2037? So with that kind of analysis, he comes up with this kind of plot where each of the data points is an MRE. He cuts off everything at luminosities of 1 gigaparsec, because that's kind of the sensitivity limit with X-ray detectors, we think. And the color is showing you the signal to noise of LISA, assuming these are extreme mass ratio in spirals. So the important thing to take away from this plot is that in order to be detectable with LISA in 2037, 2040, the time scales that these systems should have now is on the order of a few tens of minutes to a few hours. So if you can identify these systems now, they have the best chance of being detectable with LISA in a decade plus from now. And that's really interesting because that tells us kind of what time scales we should be looking out for if you want to detect them with LISA. So here's an example of a QPE source that I showed you earlier. There's a huge amount of XMM data for this source, over 11 years of data. And what Shubham did is he took the period from 2007, which is the number that you see there, and in 2018, it's reduced by a small amount. And if you assume that this reduction in period is from pure GW gravitational wave emission, then you can figure out the mass of the secondary and also the expected signal to noise with LISA. So these are the kind of numbers he gets. So the point is, under this simplified assumption, this particular source could potentially be detectable with LISA, along with, obviously, the X-ray signal. So we're just beginning to do this kind of analysis for these systems. Hopefully, we can apply this methodology to for all the other things in the sample. So in the last 3 minutes, I want to talk about prospects of detecting more. So as I said, we are in a very early stage of this field. We only have about a dozen systems at present. And we want to detect more, right? If you want to mature this field, you have to detect more than a dozen. So what are the prospects of detecting them? There's two ways to detect them. One is an all-sky survey, blind survey, like Rosita, Einstein probe, Swarm. You just go, look around, sample the different time scales, and then search through blindly. The second idea is that now that we've established they are detected after some sort of a nuclear outburst, you know where to look. So you can simply follow up the ones that are detected by ground and then see if you can detect these repeating signals. So this plot is meant for the observers, people who work on missions. So here are the kind of numbers you get if you take the E rho zeta luminosity function derived from only 4 data points. This was a paper published a couple of years ago using, again, 4 systems. And if you can get down to a flux sensitivity of 10 to the minus 12, the prospects of detecting QPs are not that great, only a few per year. However, if you go down by a factor of 10, you can really get into numbers where it's statistically possible to do science. Of course, you can get down to like excellent sensitivity kind of level, then you'll be detecting hundreds of these events. So for the blind search, the future outlook, unfortunately, because of lack of E rho zeta, the only 2 options right now are Einstein Pro and Schwamm, which are both Chinese-led missions. So if you crunch these numbers, my understanding, maybe this is incorrect, but the best sensitivity you can get down to is on the order of 10 to the minus 12. As you saw from the previous plot, with 10 to the minus 12, you're at luck of detecting maybe just a few per year. So maybe the prospects are okay, but that's something to discuss with the Einstein probe folks and also Schwamm. So in my opinion, the best way forward, at least in the near future, is to follow up Rubin tidal disruption events. So Rubin is expected to detect hundreds or even thousands of tidal disruption events. So all you have to do is follow them up with sensitive X-ray telescopes like Swift, NICER, XLM Newton, and some fraction of them, we don't know what fraction of them will have these repeating signals. The fraction of them that has these repeating signals will depend on the lifespan of these QPs or quasi-periodic interruptions, which is right now very uncertain. If they last for 10 years, then 1 out of 10 TDEs should have these repeating signals. If they last for 100 years, every TDE should have these signals. So yeah, like I said, that's the point I was trying to make. Yeah, so now is really the time, as Rubin is going to be starting full operations next year, to study these systems. So the final takeaway is I've presented to you a new class of repeating soft X-ray transients from minutes to a month timescale. They could be from orbiting objects or some unknown physics. The jury is still out. And if they're orbiting objects, then there is potential for multi-messenger astronomy in the coming decade. And if there's one thing I want you to take away from today's talk, it is this. Typically, when people are presented with the supermassive black hole accretion disk paradigm, they show you a black hole, a black dot at the center, and some sort of accretion disk. But I think it's time to change this picture to something like this. It's probably more chaotic with like stars zooming in and out of the disk. So yeah, thank you.
Thank you for this very nice presentation. We have a time for one short question. There are so many hands. Maybe just here, but we can continue during the lunch also.
Thank you for the nice talk. Is there a correlation between the period of the oscillations and the mass of the central object?
Awesome question. No, there's all of these masses, the dozen or so objects, are between the M sigma masses are between 10 to the 6 and 10 to the 7. And as you saw, the periods go from minutes to 20 days. And they're like, there's no correlation.
Thank you. Thank you very much. Let's thank the speaker once more. If there are more questions, we can ask during the lunch. So next presentation is Fermi and Rosetta bubbles as a release of the past activity of the galaxy's central black hole.
Organizers, please move to
I'm Carrie Wang from the National
Can't hear
Tsinghua University in Taiwan, and it's my great
on the
pleasure to
Zoom.
be here to share with you what we understand about the Fermi and Eurosita bubble in the Milky Way galaxy, and what we've learned over the past decade or so, and the current status. Okay, so the background image here is a beautiful image of our Milky Way galaxy that we know and love. And this is the home of our solar system. And a lot of great breakthroughs in astrophysics started right here.
We can't
For example,
hear
about 2
anything.
decades ago, by observing the stellar orbits around the galactic center, we find that there's one supermassive black hole at the center of our galaxy. And now, thanks to the Event Horizon Telescope observations, nowadays we actually have direct imaging of things that's in the vicinity of this Sagittarius A star. And because it's the closest supermassive black hole in the whole universe to us, so by observing Sagittarius A star, we hope to learn a great deal about supermassive black hole accretion and feedback activities in general in the universe. However, Sagittarius A star, unfortunately, is currently very, very quiescent. So for a long time, we actually thought that our Milky Way galaxy is probably just a really normal, boring galaxy. However, as what we will see, actually, the following discovery have made people very, very surprised. Okay, so again, this is the optical image of our Milky Way galaxy. But now imagine that your eyes are gamma ray sensitive, then this is what you would be seeing. So these are the Fermi bubbles. The height of these two bubbles are about 50 degrees on the sky, so roughly about 100 full moons lining up in the sky. That's how big these bubbles are. And the width is about 40 degrees. The gamma ray is observed in the gamma ray band between 1 and 100 GeV. The integrated gamma ray luminosity is 4 times 10 to the 37 Ergs per second. And you can see that these two bubbles are roughly symmetric about the galactic center, suggesting that they might originate from some energetic outburst that happened sometime in the past from the galactic center, such as nuclear starburst activity or an AGN activity from the Sagittarius A star. And this is the true image of the Fermi bubbles that's revealed by the Fermi Gamma Ray Telescope in 2010. And because it's so close to us, so we actually have many, many good spatially multi-wavelengths of spatial data. So in addition to the gamma ray band, we also have the X-ray image, microwave image, and the polarization data. So by combining all these spatially resolved multi-wavelengths of spatial data, that allows us to put very stringent constraints on the formation mechanisms of these giant bubbles in our Milky Way galaxy. Okay, so in order to understand the physical origin of these galactic bubbles in our Milky Way, we first need to understand what are the observational constraints. So let me describe to you what's available in terms of multi-messenger observational data. So first of all, again, this is the gamma ray image of the Fermi bubbles. And like I said, it's roughly symmetric about the galactic center, so it suggests that it originates from some energetic outbursts that happen at the galactic center. And the gamma ray comes from the cosmic rays, the high energy cosmic relativistic charge particles. So the morphology of these Fermi bubbles tells you the distribution of the high energy cosmic rays. And finally, very importantly, we also have the gamma ray spectrum. So what you can see here is that the gamma ray spectrum is very, very hard. It follows a spectral index of -2. So it suggests that these gamma rays are coming from very energetic cosmic rays that haven't cooled yet. So if you assume that the gamma ray comes from leptonic emission, for example, cosmic ray electrons due to inverse Compton scattering or something, then this cooling time of these high energy electrons, which is about million years or so, tells you that the evolution timescale or the formation timescale of these bubbles must be within a few million years, assuming leptonic emission. Okay, so please keep that in mind because we'll come back to this point later. And in addition to gamma ray, emission, we also have counterpart emission in the microwave sky. So it's first identified by the WMAP and then later confirmed by the Planck. That after reviewing the galactic plane emission, you can see a haze emission that's also coincident with the gamma ray bubble. And also the spectrum of these microwave haze emission is also very hard. So basically, it suggests that both the Fermi bubble and the microwave haze might originate from the same population of cosmic rays. And in the X-ray band, originally more than 2 decades ago, we have this all-sky map observed by the ROSAT mission. And here, basically, X-ray emission comes from the thermal branch-line emission of our hot ionized gas in the Milky Way halo. And you can see that the gas distribution in the Milky Way is just very, very complex. But here, already from this map, by overlaying the contour from the gamma ray bubble, we already know that within the gamma ray bubble, it seems to be less dense. So it suggests that it's an underdense bubble. And also there are some bright arc emission that's coincident with the edges of the Fermi bubbles. So it suggests that it may be due to some compressed gas density along with the shock that's propagating outward because of the bubble expansion. And of course, nowadays, we have the much better sensitivity now, thanks to the EROSITA mission. So like Professor Sunyav talked about this morning, we have this beautiful image of the X-ray sky right now, thanks to the EROSITA mission. And in addition to all those point sources, which are themselves very interesting, one of the most prominent feature in the new and updated X-ray sky is the EROSITA bubble. And you can see that the EROSITA bubble are again symmetric about the galactic center, and it extends to 80 degrees above and below the galactic center, so even larger than the gamma ray Fermi bubbles. Okay, and because of the symmetry and also similar morphology to the Fermi bubbles, so it might originate from the same energetic outburst at the galactic center. And in the even higher energy gamma ray band, in the TeV band, we also have some constraints coming from the Hawk Observatory. So what you can see here is the gamma ray spectrum of the region within the Fermi bubbles. The blue dots, data points, represent the Fermi data, and the black upper limits represent the constraints coming from the Hawk Observatory. So far, no TeV emission have been found. And therefore, you can see that some of the models are already ruled out. In particular, if you assume that the gamma ray, GeV gamma ray emission comes from hadronic model, which typically extends to PeV energies, then those purely hadronic models extending to PeV energies have been ruled out by the Hawk upper limits. And in terms of multi-messenger perspective, we also have some estimated neutrino fluxes coming from the region surrounding the Fermi bubbles, and the red upper limit there is the estimated neutrino flux obtained by the references there. So basically, we also find that so far, no Fermi bubble neutrinos have been detected, and their upper limit is consistent with the Hawk upper limits in the TeV band. So it again suggests that the purely hadronic models are disfavored. All right, so let me just put together all the available observational data on this simple schematic diagram. So originally, as detected in 2010, we have the blue color representing the gamma ray Fermi bubbles. And we also have the microwave haze emission that's coincident with the gamma ray bubble. And the ROSAT satellite revealed X-ray arcs that's embracing the Fermi bubbles. And now we have a much more extended EROSITA bubble that's extending to even further away from the gamma ray bubble. And so far, no TeV gamma ray or neutrinos have been detected associated with the Fermi bubbles. Okay, so just from this schematic diagram, you can see that we have many, many good observational data. So it has been really challenging for any theoretical models to reproduce all these observational data. All right, so it comes to the main question of my talk. So what is actually the physical origin of these gigantic bubbles? So in terms of the theories, what people have been trying to answer are the three following questions. The first question is, what are the emission mechanisms? So like I said, it can be either leptonic, which means that the gamma ray could be mainly produced by inverse Compton scattering of the photons within the Milky Way, inverse Compton scattered with the Casimir electrons contained within these bubbles, therefore generating gamma ray emission. And on the same, at the same time, the Casimir electrons can gyrate around magnetic field lines within the bubbles, therefore producing the synchrotron emission in the microwave band. Okay, so this is how you can get both the gamma ray emission and the microwave emission using the leptonic model. Alternatively, you can also produce the gamma rays using the hadronic emission. So there, in the hadronic process, you have Casimir protons colliding with the thermonuclei in the ambient gas halo in the Milky Way. And the decay of neutral pions will give you gamma ray radiation. The decay of charged pions will give you charged muons, and then secondary electrons and positrons that can then produce the microwave haze emission. Okay, so that is the alternative scenario for reproducing the gamma ray and microwave haze emission. And the second question people want to address is what activity at the galactic center triggers the event? So like I said, the main models that people have been considered in the past decade involves either nuclear starburst activity or AGN activity. And finally, we want to understand where are the Casimirs produced. So it can be either produced very close to the galactic center and then transported to large distances away from the galactic center, or they can be in situ accelerated by shocks or turbulence at the bubble surface. And note that not any of these combination of models would work because we have the constraints coming from the hard gamma ray spectrum. So let me elaborate in this slide. So basically, say if you want to come up with a model that uses starburst winds to transport these Casimir rays out to large distances, then because typical winds travel as hundreds of kilometers per second, so it would take more than 10 million years to transport these Casimir rays out to further distances. And 10 million years is actually longer than the cooling time of high energy electrons. And therefore, in this model, if you want to invoke starburst winds, the emission needs to be dominated by hadronic emission. So let's call it the first category of model, hadronic wind models. And alternatively, say if you want to reproduce the gamma ray bubble using leptonic scenario, then AGN jets that travels greater than thousands of kilometers per second are then needed to transport these Casimir electrons from the galactic center within a few million years before they cool. Okay, so that is the second category of models. That's called leptonic jet models. And thirdly, if you want to bypass all the age constraints coming from the cooling time of high energy electrons altogether, then it's possible to invoke in situ acceleration models where the Casimir electrons are basically accelerated at the bubble surface by shocks or turbulence. Okay, so basically, since the Fermi bubbles were discovered in 2010, like dozens of models have been proposed. However, all those models basically need to fall into one of these three categories because we have the hard gamma ray spectrum constraints. Okay, and because in this talk, due to the limited amount of time and people are hungry, so I will not go into the details, but I will just provide you with a summary of what we learned over the past decades about these three categories of models. So first of all, it's found that the hadronic model basically is disfavored, and that's because, like I said earlier, it's basically inconsistent with the Hawk upper limits in TeV and also IceCube data, the neutrino upper limits. And also, it's also found by several other studies that if you want to match the gamma ray emission using the hadronic model, then the spectrum that you predict for secondary electrons population is not enough to match with the microwave haze spectrum. Okay, so basically what's found is that the hadronic wave model is disfavored in terms of explaining the Fermi bubbles. However, the other two categories based on previous simulations, actually we found that the gamma ray and microwave emission can be simultaneously reproduced, both for the leptonic jet case, that's what I've been working on for the past several years, and also the in situ acceleration model can also reproduce the gamma ray and microwave emission quite well. Okay, so then, and of course you will have this question, so whether the leptonic jet or in situ acceleration model is the correct one. So let me come back to this segmented diagram again. So comparing these two models, like I said, in terms of the non-thermal emission, they reproduce the data quite well, equally well. However, there's one key difference between these two models, which is the location of the shock wave. Okay, so in the in situ acceleration model, because it's assumed that the cosmic rays that generate the gamma ray emission is accelerated by shocks and turbulence in the shock downstream. So by construction, the shock surface needs to be identical to the Fermi bubble surface. On the other hand, for typical AGN jet inflated lobes and bubbles, typically what we have is a much more extended shock wave that's much more extended than the contact discontinuity that contains the jet material ejected from the AGN jet. Okay, so by comparing these two models, basically we need to identify the location of the forward shock in the system. And how do we identify the shock? We can look into the X-ray band. Okay, so of course the Rosat map, if you look at the X-ray arcs and also the contour of the gamma ray bubble, it's really hard to tell whether the shocks are coincident with the bubble edges or not. But now we have a much better look in the X-ray sky provided by the Erosida mission. And if we overlay these two images, the red represents the gamma ray image and the cyan represents the Erosida bubble, then you can clearly see that these two surfaces are not the same. And one of the most likely scenario is that maybe the Erosida bubble traces the forward shock due to the bubble expansion, and the Fermi bubble is the contact discontinuity between the jet material and the ambient ISM. And in order to test this hypothesis, I ran customary MHD simulations of the bubble formation, assuming that they are triggered by some jet activity of Sagittarius A star. And because we want to model the multi-wavelength spectra of this system, so we used spectral evolution code for describing the evolution of a customary spectra within the simulations. And so in the beginning, we assume that there's a jet activity that happens perpendicular to the galactic plane. And with the injected cosmic rays, we assume that the injected spectrum ranges from 10 GeV to 10 TeV with a spectral index of -2. And after injection, we just let the cosmic electrons cool due to inverse Compton and synchrotron cooling due to interaction with the radiation and magnetic field within the galaxy. So here I'm just showing you one short animation made from my customer MHD simulations. So here you can see the evolution of the gas distribution and cosmic distribution due to the initial outburst. So here the white and red contours represents the distribution of cosmic rays, and also the cyan represents the distribution of gas within the Milky Way halo. And in the simulation, we take into account the dynamical interaction between these two fluids, between the cosmic rays and the thermal gas. And at the end of the simulation, we can then self-consistently calculate what's the predicted amount of the multi-wavelength observational spectra. Okay, so here I'm showing you the result. So basically what we found is that all the X-ray, gamma ray, microwave data are really well matched by this simple AGN jet model. So here you can see the predicted X-ray map overlaid with the gamma ray map. in the upper left corner there. And in the bottom left, we have the broadband spectrum also provide pretty good agreement with the data. And also on the bottom right, we have the profile in the microwave band and the profile in the gamma ray band. So the good agreement with the multi-wavelength observational data suggests that the Fermi and Eero-theta bubble might be relics of past activity of the galactic center supermassive black hole. And from our simulations, what we learned from our parameter set is that the jet has occurred about 2.6 million years ago. It was active for 0.1 million years. And during its active phase, the inferred attendant ratio is about 1 to 10%. And interestingly, the time scale and the energetics that's found by matching the multi-wavelength observational data is actually consistent with another independent measurement from looking at the ionization cone in the Magellanic Stream. So basically, I won't go into the detail here, but these works have found enhanced H-alpha and carbon-silicon line ratios, suggesting that our Sagittarius A star might have gone through a past Seyfert flare activity before. And the inferred energetics and also the timescales are consistent with our model as well. Okay, so both of these models have suggested that maybe the Sagittarius star really once had an elevated activity a few million years ago. And so far, this leptonic jet model seems to be quite promising in terms of explaining the multi-wavelength observations of Fermi and Eero-theta bubbles. But of course, I'm not claiming that everything is resolved. Of course, there are many still some open questions that are listed here. So first, do the jets need to be perpendicular to the galactic plane? Okay, so in my previous simulation, motivated by the symmetry of these observed bubbles, I always just initiated the jet perpendicular to the galactic plane. But we know that AGN jets typically is dominating, or the direction is determined by the black hole spin axis, which does not need to know anything about the galactic rotational axis. And therefore, it will be interesting to explore the possibility that the jet might be tilted, not perfectly perpendicular to the galactic plane. And therefore, in a more recent study, we explored the possibility of a tilted jet interacting with a dense clumpy galactic disk. And what we found is basically that with the interaction with the dense galactic disk, it's possible that the tilted jet, due to the jet dissipation, will dissipate its kinetic energy, form a hot bubble that expands outward isotropically, forming a symmetric bubble as the observed one. Okay, so basically in this new study, we found that the tilted jets are also a plausible solution for creating symmetric bubbles. However, if you look at the time scale in the simulation there, the time scale is roughly like 12 million years, which is again longer than the cooling time of high energy electrons. So for this model to work, we actually need some additional acceleration of the Kashmiris within the bubbles to self-consistently explain the high energy part of the gamma ray spectrum. Okay, so this is about the tilted jet model. And the second question is, of course, now we find one solution, but of course, this is probably not the only solution to the whole problem, right? So what are the alternative scenarios? So people have considered things like AGN winds also. And for previous simulations considering AGN winds, typically the formation time of these bubbles are also on the order of 10 million years, which is longer than the cooling time of Kashmiri electrons. So for these AGN wind models, they also need some reacceleration that happens within the bubbles to self-consistently explain the high energy gamma ray spectrum. And Professor Ruffini have mentioned about the possibility that maybe the Fermi bubbles are remnants from a previous GRB activity. So this is really a brand new idea, and I will be really curious to discuss more about this possibility. And so far, because of the similar morphology of the Fermi and Eero-theta bubble, so we've been considering one single energetic event that reproduce both bubbles. But of course, it could be actually due to two different events, independent events. Of course, it will be harder to constrain from the theoretical point of view, but it's certainly a possibility, especially if you were in Jen's talk last evening. Then he actually mentioned about the possibility that the Eurocilia bubble could be driven by magnetized outflows related to star formation activities in the Milky Way galaxy. Okay, so that is certainly something that we will consider in the future. And finally, so we ruled out some models based on previous modeling, but how could future observations further distinguish different models? That is the key question. Okay, so in the future, what we look forward to is possibly obtaining more and more stringent constraints in the TeV band and also the neutrino fluxes. And therefore, we can have a better idea about the high energy cutoff in the gamma ray band. And also in the future, we will also possibly have some MEV observational data that can help us to distinguish the leptonic and hadronic model because of the threshold for pionic decay. And also possibly in the future, if we can determine the turbulence level within the bubbles using spectral lines, etc., it will be very helpful for constraining these different models as well. Okay, so in summary, the multi-messenger observations of the Fermi and Eurocilia bubbles provide us very stringent constraints on the formation mechanisms of these fascinating structures in the Milky Way. And the multi-wavelength spectra of the Fermi bubbles and the microwave haze suggest that the bubbles and haze are dominated by leptonic emission. And our customary MHD simulations suggest that the Fermi and Eurocilia bubbles are likely caused by a single hour burst of jet activity of Sagittarius star about 2.6 million years ago. But future observational data will provide us better and better understanding of the physical nature of these bubbles. I'll stop and thank you very much.
Thank you very much for this nice presentation. We have time for one short question.
Oh, ask for question. I make a statement.
Okay, question. But there are two. Well,
What's your estimate of the mass of the AGN in the Milky Way? How much? The recent ones.
Right. So in our model, we actually assume that the mass of the central supermassive black hole is 4 million solar masses. And then if we believe that, then the required energy is about 1 to 10% of the Eddington rate. So if you change the mass, then it will change the. Mm-hmm.
And each of them are what? The black holes? Deep black holes?
No. There's we assume there's just one single black hole, the Sagittarius star. We are focusing on the main bubble that's driven from the galactic center. Right.
Another statement by Professor Ruffini.
Just a short statement. We presented the diagram. We are thinking about something happening not so far back, but 5,000 years ago. And we will be very happy to discuss with you the details. Thanks.
Thank you.